day 3, session 3, and we will now dive into the hologram with Daniel Jafferis from Harvard University. Over to you, Daniel.
All right. Okay. Well, thank you so much for the invitation to speak. I wish I could be there in person in Madras. I'm sure everyone feels the same. So today I'm going to tell you about some work that I did with Pro Slam Pro, which we provocatively titled Inside the Hologram. And so first I'll give you some general introduction about what's the goal and why is it interesting to try to get inside the bulk and how we propose to do that. And the main idea will be to use as a model of a physical observer a black hole. A black hole might sound like a strange observer, but it's much simpler to understand than anything else. And I'll use that to get some way to evolve operators in the vicinity of a black hole into the interior in some universal way. And it works perfectly in some very special class of states. And then more generally, there are corrections to this geometric picture, which I will describe. And then I'll discuss various checks of the idea and some interesting places where you can apply it, where perhaps surprisingly, it still seems to work and give sensible results. And then I'll wrap up with some future directions. So, of course, as we all know, quantum gravity and at the de Sitter space is equivalent to an ordinary gauge theory quantum system living on the boundary. And in this dictionary, the simple operators, at least, of the quantum mechanics or the quantum field theory are extrapolations to the boundary of bulk operators. And that's true for local operators, like the stress energy is the boundary limit of some component of the metric, but even things like Wilson lines, those create strings that propagate in causally from the boundary. So even the Wilson loop operator on the boundary will commute with bulk stuff, which is space-like related. And really, the only reason why the theory captures the interior at all is because of the Hamiltonian constraint equation, which tells you that you can't quite separate the interior from the boundary. So it's a bit subtle, right? Now, sometimes we kind of ignore the ADS interior and we think of the whole story as, ADS string theory being some maybe approximate or exact. It's something like an emergent method that computes boundary quantities. And for that, it's extremely useful. It's some semi-classical emergent semi-classical property of large gauge theories. But in fact, we live in the interior of a gravitating space-time in our real world, so we don't have the luxury of taking that interpretation that the gravitating interior is just the intermediate step in the computation because we seem to live there. So this motivates, of course, the idea of finding how bulk observables are really encoded somehow in the dual gauge theory. And although, of course, a lot is known about this question, it's still really a difficult open problem, especially in cases without special symmetries where, if we just want to make a single field excitation inside of empty ADS, well, everything is governed by the isometries. But in general, we don't really know the procedure. And there are sort of several types of problems. There are some practical problems. We just don't know a universal formula, if you like, for constructing the bulk operators, even if we're told that the theory has some particular dual. For instance, if it looks like Einstein gravity up to some energy, we don't automatically get a formula for what, the bulk metric at some dressed operator in the interior looks like. And then there's a kind of conceptual puzzle, a problem, which is that in all of the methods for describing bulk observables in terms of the boundary that we know, it seems like you need to solve the bulk theory in the interior first. So the well, one method of trying to do bulk reconstruction is that you just use the equations of motion of the bulk theory, some gauge, and evolve the operators in. Of course, that obviously involves solving the bulk theory first. And then there are also these quantum information or entanglement-based reconstruction methods. They have told us a lot about where in the boundary information about what is encoded. So these entanglement wedge reconstruction results tell you that if you want to probe some operator in a particular location in the interior, then it can be encoded by boundary operators that are in a region where the entanglement wedge of that region contains the bulk point and so on. But it doesn't give you the formula for how to write the operator. It just says that the information is there. And if you actually want to write the operator, you need to know what operator you're talking about. And again, the basic method is that you solve the bulk, you compute the matrix elements of the bulk observable that you want to talk about, and then you reverse engineer them. So that's okay, although it might make you wonder whether, what exactly is the input and what is the output. And then there are also, in addition to the practical and conceptual problems, also paradoxical problems, or paradoxes, if you like, which occur when you have horizons in the interior. And so the puzzle is really the physics behind the causal horizons can depend on signals that come in from, say, other boundaries. If you have a two-sided black hole, and they don't even appear to be part of the data that you were given. So there's this moral wall, a two-sided black hole. I jump in from the right, and somewhere behind the horizon, we might look at some bulk observable there. We can think about it as just a bulk operator that's dressed to the right boundary, by shooting some geodesic, for example. And the question is, well, it seems puzzling because you can't, no operations purely on the right can ever detect whether you throw this thing in from the left by unitary transformation or not. It's just impossible if you live only on the right. And if the observable is framed to the right or made by a person who jumps in from the right, it's hard to understand where they get the data for determining the answer to this question. So this kind of, so this is really the sharpest problem, but it also feeds into the conceptual and practical issue, because if we get a contradiction, then there's no surprise we don't have a formula. And now there are really two slightly different questions about, or rather different questions about what we mean by trying to reconstruct the bulk of the interior. One of them would be a question about operators that act on the global Hilbert space. We have Hilbert space of the whole quantum gravity and the whole space-time, and we might try to talk about linear operators that act on this Hilbert space. And since the ADS-CFT duality is true, if you do it correctly, you have to reach the same answer as the CFT, and you'll find that you will get the same CFT operators, and there's nothing else to say, of course. And the resolution of these kind of puzzles, like why is the right framed operator there able to detect whether or not some junk is thrown in from the left, really come because the bulk operators have to obey the Hamiltonian constraint equations non-perturbatively. And that means that they require input that you might not have realized just to define them. And this is the story that's not entirely complete, but recent work on replica wormholes also gives us some hints how that picture should fit together, but that's not the thing I want to talk about today. And today I want to talk about a different question, which is how do you describe the experience of physical observers when they enter the interior of the space-time? So, of course, we could try to make a human being out of the degrees of freedom of n equals 4 super Yang-Mills, but that sounds very difficult and hopefully it's beside the point. So what we want is a good model for an observer, and what I will use is a black hole, which we think of as a probe of a much larger space-time. So we have a big ambient space-time that we're interested in, that's the system, and we throw in a comparatively small black hole from near the boundary where we understand things and let it evolve and see whether we can use that to understand the interior. So a black hole is a pretty good model for an observer. Black holes are localized. And not only they localize as classical objects, but their wave packets and position space remain localized, actually for the large black hole indefinitely because of the interplay with the ADS potential. They're stable and they're universal in any theory with gravity. So sounds like a great thing to use. And more importantly, for the story I'm going to tell you, that black holes have approximate near horizon isometry, the Rindler or Schwarzschild time translations. And that will allow me to define evolution of operators near the black hole with respect to that approximate isometry, which you can identify with the proper time measured by this black hole observer. Now, of course, that's in principle a feature not only of black holes, but of any massive object. But of course, it requires that the Schwarzschild radius is larger than the Compton wavelength if you want this approximate region to be very close to the Rindler-like isometry and not receive all sorts of corrections which are non-universal. So that basically means that you'll want to talk about a black hole. Now, this idea makes something precise, which might have sounded very vague. If we want to discuss ADS-CFT from the reference frame of an observer inside, what do we mean by those words, right? In quantum mechanics, we never know, or we don't really know in general in quantum mechanics how to describe it from the reference frame of something inside the system. We always imagine there's an external observer. How do we get an external observer inside the space-time? So, you know, if we were in QFT, we can just couple an external apparatus anywhere in the space. But in gravity, that's not allowed because it won't satisfy the constraint equation. You have to somehow physically throw it in. That's the whole difficulty. But here we can take our probe black hole to be maximally or thermally entangled with the reference system. We imagine the reference system is another copy of the same CFT. And then that entanglement is, of course, geometrically realized by the wormhole between them. And now we have, this gives us a precise meaning to the reference frame of the observer when they're in the interior of the original space-time. It corresponds to discussing gravitational observables that are framed relative to the reference ADS boundary. So I can shoot a geodesic from this reference boundary. It goes through the horizons or the bifurcate point into the interior of the space-time of interest. And that's what we should think of as the observable relative to an observer. So here's a cartoon of the setup. This was kindly produced by my collaborator, Lampros. You can see the difference in quality of the pictures. The ones that look like they were drawn by a small child or mine. So we have this system here depicted in the left part of the figure, and then the reference sits over on the right. And we can put the, we imagine that the space-time looks on the reference side just like the usual empty, or the usual ADS Schwarzschild with no perturbations. And then on the system side, it's a black hole probing this ambient space-time. Okay, and then I'll often discuss some operators that are in the vicinity of the black hole that I'll call the atmosphere, and you can think of that as about several times the Schwarzschild radius, for example. Okay, so but the atmosphere is supposed to be a region of the space-time containing the probe black hole, which is, at least for accepted cases that we'll discuss explicitly, approximately isometric to the local neighborhood of ADS Schwarzschild without the rest of the perturbations that make up the background of the system. And so that will be true as long as the black hole doesn't move too quickly or the atmosphere is too large and so on. So, and more precisely, let's imagine that the system state, that is the semi-classical space-time that we wanted to probe, is produced by acting with this unitary operator U on a vacuum in global ADS. And now we can conformally translate it so that it's all pushed to one side of global ADS. And then we're going to put it in a black hole very far from where all the stuff is that made up the space-time of interest. So equivalently, we want to throw in the black hole from near the ADS boundary. So we put a translation in between the unitary and the thermofield double state. Of course, the thermofield double state puts the probe black hole in the center of ADS, but now I push it all the way over to the edge with the translation, and then I act with this unitary. And so for any particular U, I can always pick A large enough, so I throw the black hole in far enough toward the boundary that the effects of the black hole are arbitrarily small in the region where U, which built the non-trivial spacetime, acts non-trivial. So for example, the gravitational field produced by the probe black hole as measured by the boundary stress tensor can be made arbitrarily small in the region of the boundary where the unitary U acted non-trivial. Okay, so that's just saying we can decouple the interesting space-time from the probe by throwing it in from close to the boundary. And now the key point, which is somewhat really simple, is that for such a probe black hole, the modular Hamiltonian, which is, as you know, the thing you get by tracing out the reference. If I trace out the reference, I will get a density matrix of the system. And then I take the log of that density matrix minus the logarithm of that density matrix. That's the modular Hamiltonian. As you know, for the thermofield double state, the modular Hamiltonian is the ordinary Hamiltonian. So on the reference side, because the unitary didn't act on the reference, the modular Hamiltonian would trace out the system. So how the modular flow looks on the reference side is literally the reference Hamiltonian, normalized by the inverse temperature beta. On the system side, it's conjugated by this unitary that produced the interesting spaceline. So K system is U, H, U dagger. But even that general modular Hamiltonian will act locally near the bifurcation point or near the extremal surface, and therefore near the horizon of the probe black hole, like the local Rindler or Elias-Schwarzschild, if you like, evolution close to the black hole. And of course, that is exactly the proper time evolution along the trajectory of the black hole in thinking of it as a localized particle moving in this enormous ambient space. Okay. Now, you might sound a little funny that I'm using a large black hole, a thermofield double state, as a probe object. We usually think of the black hole as big and something else probing a black hole. So you might ask, why don't I try to use a small black hole or even particle, something else? Small black holes at first sound like they might work. They can be prepared in the microcanonical thermofield double state, so we can still have them nicely and geometrically entangled with a reference. They dominate the microcanonical ensemble down to some radius, which is parametrically smaller than the ADS radius. And just by comparison, in our universe, we take the ADS radius to be the Hubble scale, then the radius of the smallest microcanonical black hole is a couple hundred meters. So it's not terribly large. That does sound like a reasonable probe of a cosmological space-time. And the thing where it has the microcanonical thermofield double given by the entangled state written there with some appropriate envelope function f of v. Then I act with U system on this microcanonical thermofield double, same setup. And I put e to the minus v in that for fun. If the envelope function f of v is narrow enough that it doesn't become dominated by the canonical ensemble, but not too narrow, so that there's still a geometric dual of the state, right? You don't want to project onto, say, a single energy microstate, then you will not have the connected smooth Einstein-Rosen bridge, as was discussed in a paper by Merle not too long ago. Then everything seems like it can work, and in fact, the modular Hamiltonian in this case will be basically B times the Hamiltonian if the envelope function is chosen as a simple Gaussian. That will be the case over most of the subspace of interest where we act with some simple operators on top of the state that we're talking about here. But the problem is it's not that. The problem is that this state, this microcanonical thermal field double, has a black hole wave packet spread out over other ADS scales. Because now the size of the black hole is much smaller than the ADS radius. And so its position space wave packet, if you wait long enough, naturally spreads as any wave packet of any particle, and will spread out to something of the size of the ADS scale. And it's the smeared thing, which is the microcanonical thermal field double. Similarly, if we have really ADS times an internal manifold, then this small black hole will be smaller than the internal manifold, but its wave packet will be smeared out in the internal manifold. So that's not nice. That will not allow us to understand the action of the modular Hamiltonian geometrically, because it's not a semi-classical state. So you could project to a localized state, but if you do that, then you'll have a more complicated modular Hamiltonian, which could be analyzed, but we didn't do that. And so some more refined analysis is needed, and that's what you need to see sub-ADS scale locality. Because we only use big black holes, we really only see locality of the space-time at scales much larger than the ADS radius. And presumably that's why we didn't need to use any special properties of the dual theories, such as a large higher spin gap or a structure or a lack of any internal manifold and so on. Okay. How am I doing on time? When I maximize it, I lost my clock.
Yeah, you're doing fine. You have just spent 15 minutes.
Okay. Yeah, good. Okay, thanks. Wait, is there some black rectangle now? In the top?
No, it's fine. It's fine.
Oh, good. Okay, I see a little black rectangle. That's not. Right.
Indeed, there is one on top. There is one on top, but it's fine, I guess. I mean.
I see. Okay. I think it will probably go away. It's from Zoom itself, amazingly. Oh, if people wrote me a question in the chat, I haven't seen the chat.
Okay, a black rectangle is now appearing in the. Okay. Well, if there is a question, people can interrupt and yeah.
Okay, good. Yeah. Please.
If you pause and take questions, people can ask if you want to take questions. Yeah.
Yeah. Good. Yeah. People should just interrupt me and ask a question. I would be very happy with that. Don't feel shy about.
Sure.
Just talking. So great. So what was I saying? Right. So we want to. So the idea is that we start with the probe black hole near the ADS boundary, and near the ADS boundary, we know how to construct bulk operators in the atmosphere of this black hole. And then we want to evolve them using the modular Hamiltonian. And the resulting operator is like Heisenberg picture operator that's just translated along the probe black hole's trajectory. And that statement will be true as long as we consider acting this operator only in a certain subspace of the full Hilbert space. Of course, if we acted on some totally different state that has nothing to do with the space-time that we started discussing, it might act in some unknown and complicated way. So we always have in mind that we take the initial state we're talking about, which includes the probe black hole, and then we act on it with the simple operators of the ADS system to produce what is sometimes called a cold subspace or little Hilbert space of simple of states which look like quantum field excitations or bulk effective field theory excitations on top of some given background spacetime. And so it's in that Hilbert space that the operators will act in the way that I'm trying to describe. Now, we should also think a little bit about the gravitational dressing of the operators in question. We'll come back to this in some other guises. We already see the gravitational dressing maybe sounds a little unusual. The original bulk operator in the black hole atmosphere, when it was near the boundary, is dressed, let's say, to the boundary in a simple way. Now we evolve it along the black hole using the modular Hamiltonian, so it will be dressed, its dressing will track the pro-black hole trajectory. So that might seem a little unusual. But of course, when we act differently dressed bulk operators that end up inserting a bulk field at the same space-time point, if we're acting them on a particular semi-classical state, actually gives the same state up to 1/n corrections, which you could confirm by computing the overlaps. In other words, if I have a bulk operator phi1 and phi2, which have different dressings, in the state psi, it turns out, let's say, that the dressings correspond to inserting the operator phi at the same point, x, then those two states will be essentially the same state up to order 1/n corrections, which is not completely trivial because you might think that the state with the different dressing will have the gravitational fields of the phi particle that it creates going in a different place. And that is true, but when we talk about action with a single phi particle, the gravitational fields associated to it are smaller than the quantum fluctuations in the gravitational fields of the background. And so that effect is subleading, and in fact, the states are the same as states up to the 1/n corrections. So the whole discussion was restricted to a cold subspace where we can think in this way. Now, we can discuss observables, operators of the bulk theory framed to the observer or framed to the boundary. If we have operators framed to the observer, that means that they're being shot from the reference boundary. Then we evolve them just by the reference Hamiltonian, which is the modular Hamiltonian on the reference side. That, of course, just does the Ringler boost, if you like, around the extremal surface for the endpoint of the operator in the system. And modular evolution on the system side acts on the atmosphere operators, the first approximation, in the same way. So you can say it simply changes the gravitational dressing so that they get boosted relative to the extremal surface. Okay, and so these two evolutions are the same, at least when acting in this cold subspace. So this is the cartoon. We have our black hole following some trajectory. We start with an operator in the green atmosphere. We evolve it using the modular Hamiltonian to get the operator evolved up at some later time. Now, if that was the whole story, then everything would be fantastic and we just have an easy solution to the problem of bulk reconstruction. You throw in these pro black holes, you evolve along them, it's some universal prescription, and then you can read off everything. But it's not quite so simple because the modular Hamiltonian is not exactly this local Schwarzschild time evolution. In fact, that doesn't even quite make sense because the Schwarzschild time evolution is approximate isometry of the space-time with the pro black hole because of the other stuff in the space-time that you're trying to explore. And so there are two kinds of effects. The first one is sort of direct effect. If you have matter or curvature in the atmosphere region, it leads to corrections to the action of the modular Hamiltonian as Schwarzschild evolution. Because our modular Hamiltonian is conjugate of the regular Hamiltonian, if the black hole was sitting in the center of ADS, by this unitary that generated the non-trivial space-time. So the unitary U is very complicated and it's part of the data that's given to us, right? That's how we created the state. But the effects of matter and curvature in the atmosphere region, of course, are transients that decay exponentially because things in the near horizon region fall into the black hole. So unless you keep dumping matter into the probe or some difficult scenario like that, those effects are transients. And if you wait long enough, after, say, all the matter has fallen into your probe that will ever fall into it, then the operators you get by evolving in the modular time are again the correct Schwarzschild evolution, the proper time evolution that you wanted. But in the intermediate regime, when stuff is falling in, the modular evolved operator is not the correct operator, and it cannot be used, therefore, to detect the presence of infalling particles in the state. In fact, it will, if you applied it naively, you would always conclude that there's never any particles in the infalling state. Sometimes this is referred to as the frozen vacuum problem, and it appears in other entanglement-based reconstruction methods. So just for example, suppose you had some state psi where the modular Hamiltonian was K0, where there was no infalling matter into the probe. Operator O, which makes some matter, which will eventually fall in. It doesn't fall in at t equals 0, but it, here's the black hole coming in, and here's the matter, and at some later time, the matter will go through the probe atmosphere. So what you would like to compute is, say, the expectation value of the bulk operator phi evolved by modular evolution in the new state, which is e to the I lambda O psi. But of course, because K is conjugated by O in the opposite way, the e to the I lambda O's cancel out. Actually, one of them has a sign reverse, all right? So they cancel out, and you just find that you get the same expectation value before you threw in the matter. But that's clearly the physically wrong answer. So the modular flow doesn't correctly reconstruct the operators there. And I'll come back to this point at the very end. Now, there are also other effects which don't decay in proper time, which are the Shapiro delays, which change the reference frame of the black hole atmosphere relative to the extremal surface. So if we draw a cartoon like this, here's just the eternal black hole. Now the system is on the right. Sorry, the figure is flipped. Here we have our T surface. Imagine we evolve it along the Schwarzschild slices. And we have our bulk operator here at phi 0, and then it's moving up on some trajectory. But if there's an extra infalling matter, the squiggly red curve, then it will shift out the horizon. At later times, the operator denoted by phi t, which has the same relationship to the horizon as the original operator phi 0, is shifted outward relative to where the operator that you evolve relative to the RT surface will go. So in other words, when you have infalling matter, there's a shift between the horizon and the RT surface. So if we wanted to discuss operators in the black hole atmosphere, whose evolution we're trying to describe along the black hole trajectory, they are defined relative to the parent horizon, but the modular evolution will frame them relative to the RT surface. And so then there will be a discrepancy, and that discrepancy grows exponentially in modular time rather than decaying exponentially. So in other words, if we thought about framing it from the RT surface, there's a shift as it crosses the shock generated by the infalling red squiggly particle. So that we know how to take into account. Let's suppose that you knew what the true proper time evolution operator was. Let's say that between t equals 0 and time t, where little t is the boundary time, between some point and some other point on some particular slicing, there is an evolution of the operators. That's the answer you want. That's how you evolve the operators along the black hole trajectory. Let's say that's given by unitary v of 0t. Then no matter what it is, you can expand it in terms of eigenmoles of the modular operator. So you'll get the modular Hamiltonian itself with some coefficient. You might get other modular zero modes, like rotations and so on. And you can get these modes which have maximal modular chaos. So there is some, if we look at eigenmodes of the modular operator, there's, at least if we talk about evolutions that are not too many times greater than the scrambling time, then we can discuss we can classify operators in terms of their eigenvalues under the modular evolution, and there's a bound on the number here, which we can think of as a chaos exponent, which is bounded by 2 pi. So those are the ones with saturated 2 pi exactly correspond to the gravitational Shapiro delays. So we may get eigenmodes of that type, and then there are the modes that have the opposite property, that have oscillatory behavior under modular evolution, and those lead to these transients that will decay in modular time. That's the direct effects that just fall into the black hole. So, of course, in a general theory, there might be other eigenoperators, other modular eigenoperators with submaximal chaos exponents. For instance, even the one, in general, there might not even be one with a maximal exponent. And those things with submaximal chaos exponents are associated to stringy corrections that would presumably, just as in the case for usual like thermal chaos, that's not the modular case, lead to inelastic effects rather than unitary equivalence between the atmosphere algebras at 2 times. So we will assume that those are absent. So actually here is where an assumption that the theory has a dual that looks like Einstein gravity enters, rather than some stringy dual. If it had a stringy dual, we could also try to analyze it, but we simply didn't do that. But in that case, you will not even have a unitary mapping between the atmosphere algebra at early and late times, because there will be inelastic effects to strings. Okay, so that's the proposal. Any questions about the proposal at this stage? Okay, so now I'm going to give you some tests of this idea. So first, a very straightforward kind of test is to consider a probe trajectory that begins and ends near the ADS bound. In that case, of course, you know the unitary mapping between the initial and final algebras, the near probe algebras, in terms of the global ADS Hamiltonian, and maybe it comes on the other side, in rotation, whatever. But you know what this unitary is. Then you can take that D and plug it into the equation written there and decompose it into the modular part of the evolution, the maximal chaos exponents. Oh, by the way, the maximal chaos eigenoperators, of course, are angle dependent if we're in higher dimensions. So you have one for each angle on the horizon sphere. Okay, so one could carry out that procedure and extract at the proper time that way, and extract the coefficients here, this f of omegas, which are a measure of the null energy flux through the horizon at angle omega. Now, just to say, in this case, we could say things in slightly different words. In most of the talk, I work in Heisenberg picture. If you thought about the same story in Schrodinger picture, and we went back to the case with no infalling matter, then we'll discuss the time-dependent modular Hamiltonian, because the state evolves in time. Of course, it evolves in a very simple way, just by unitary conjugation by the ADS Hamiltonian. But this modular Hamiltonian defines a modular Berry-Wilson line, as was studied in papers by Lampros and his collaborators. And the way to think about it is you look at the infinitesimal change, the derivative of the modular Hamiltonian with respect to time. Looks like the commutator, of course, with the ADS Hamiltonian, but you project that onto the non-modular zero modes, because of course the modular zero modes commute with K by definition. So you project the global Hamiltonian onto the non-modular zero modes as a function of time, and then take the path-ordered integral of that parallel transport operator. That gives you the unitary transformation of the way the atmosphere algebra is embedded at the initial and final times. But now we're in Schrodinger picture, so that's not the total evolution. There's also the overall original Hamiltonian evolution on top of it, of course. So it has these two pieces in Schrodinger picture. Now, you can check that this procedure works. If you want to see the details, we read about them in our paper. For example, we can study a probe black hole of empty ADS, where we give it a series of kicks by applying ADS isometries on the state at various times. This gives you a modular Hamiltonian that receives this series of kicks. Then you can compute from this procedure, from this general formula, given how much modular evolution did you need to match the total evolution in the global Hamiltonian, and you will correctly extract from it the proper time along a general trajectory produced by a series of infinitesimal kicks. That's perhaps not too surprising. It agrees, of course, with the proper time that you would measure from a two-point function, or equivalently the phase of a state where you have some massive particle of rest mass m will receive a phase e to the I m tau, where tau is the proper time. Here we replace our massive particle with a black hole. The rest mass is replaced by the local energy, which is the modular Hamiltonian. So these things perhaps unsurprisingly agree. Of course, this is a situation where you knew the initial and final observables, so you didn't need to compute them because you started and ended at the ADS boundary, but it's a check of the consistency of this procedure.
Daniel, can we finish in a few minutes, like 3 minutes?
Oh, yeah.
Questions?
Yeah, I'm almost done, actually. Yeah. Thanks for the time reminder. One thing that you can do with the black hole that you couldn't do with the particle is that you have this this other term here that measures the amount of energy that fell into the black hole. So in a situation where there is infalling matter, again, you apply the same procedure and you can extract the amount of energy that fell in. Now we come to the most interesting part, which I'll finish up in just a couple minutes. It's only two slides, I think. What happens if you jump behind the horizon? So we have a left-right black hole. That's the big black hole. Then we make a tiny, small probe black hole. That's this line here. I hope the figure isn't too dark. That's this line here. And we want to evolve in modular evolution along the probe black hole. And the picture says it should take us behind the horizon. And that seems very puzzling because we started with the probe black hole all the way out here at the right boundary, entangled with some reference. How does it know anything about the left? How can it be that we will have a procedure which gives us the operators that are now behind the horizon, which can be kicked from the left, right? It sounds like it will make a pure right operator, and that will be wrong. However, it's not true. It works. It works because no matter how far you take this probe toward the right boundary, there will always be a small amount of entanglement between the reference system that I didn't depict and the left boundary. And so when I apply modular evolution, it does contain some left-right operators. And as I evolve long enough, their effects are enhanced, and we end up getting the correct answer. So one can see this in a very simple example. We just take ADS Rindler. So that's a cheap version of a left-right black hole. Now we just take the left-right Rindler wedges. And then we have a probe black hole that's translated very far to the right. This is a great example because we know the modular Hamiltonian for the probe of ADS Rindler. This is the translation of the global Hamiltonian. And if we translate it very far, then the leading term is this operator, which we can write in terms of the left and right Rindler generators B, and the generators P plus and P minus, which are the null translations along the Rindler horizons, which are also ADS, global ADS isometries. And now if I act that thing on an atmosphere operator, so I evolve it with this K, for long times, the leading term looks exactly like a P minus generator on phi with a small correction given by its some Rindler evolution. So that's exactly what you expect for the trajectory of this probe crossing the Rindler horizon. So it automatically produces P minus, which is a left-right operator, from the small amount of, and it got the left part because there's a small amount of entanglement between the reference and the left to begin with. That might seem a little surprising, but it's actually related to the story of traversable wormholes, where we can imagine that, how do we entangle the reference with the left-right system? We can imagine we act with something like a control gate that entangles the qubits of the probe with the reference. So if like the reference has a 0, we do nothing. If it has a 1, we flip the qubit in the system so that it will be entangled with the reference, be in the same state as the reference, roughly. If the system had started in trivial state, then it will be maximally entangled between the right side and the reference, and there will be no entanglement between the reference and the left. But that's not the case, because in the connected left-right black hole, the big black hole we started with, there is always some amplitude that the qubit that we're discussing is occupied, and that's entangled with the left. It's actually very similar to the setup of traversing wormholes, where then the probe is not a black hole, but a single particle. And the small amount of entanglement with the left is crucial to being able to traverse the wormhole. And when you act later with the left-right coupling, it makes it into a causal signal and enhances it. But if that was 0, it wouldn't work. And so something similar comes into play here. So that's really all I wanted to say. I had a few words of future directions, but maybe since I'm out of time, I'll skip it unless somebody asks me. And let me just summarize. So the idea was that we can throw in a pro-black hole and to a space-time of interest to give some universal prescription, at least in certain class of states, where say there's no matter that would fall into the probe, for how to evolve the nearby operators into the interior. So it's some universal reconstruction procedure. The modular time along the trajectory of the probe is measured by the modular clock, corrected by superior delays associated with modular chaos. And it works even when the probe crosses the causal horizon. So thank you very much.
Thanks, Daniel, for this great talk. So we can take questions from now. People can just unmute and ask Daniel. Shubho has a question.
Yeah.
Hi, thanks for the talk. I just wanted to, you skipped the slides a bit too fast on the future directions. Can you just show the slide on this hitter? Can I get a preview?
Thank you very much. I'd love to.
Yeah, that's
right.
kind of...
So I think, yeah. So the most important, I think the most important thing in this program that I described is to solve the frozen vacuum problem. If we could do that, then we would have a complete. Then there would be some general procedure for reconstruction, and a first step is to at least diagnose which are the states that have no infalling matter. Okay, so at this point, the way I described it, somebody has to tell you that the state is good. There is not a I didn't tell you what to compute to check that the state will be good, where you will not have this frozen vacuum problem. So that's analogous to trying to find something like the equilibrium condition of the Papadopoulos-Raju construction. And I will make a conjecture for the answer. Let's suppose you consider the near boundary algebra collection of simple operators near the ADS boundary, and we act that on our state. Let's say our state is U psi, where U is something, let's say psi was a state without infalling matter and U does have infalling matter. A priori, we don't know how to distinguish that U psi has infalling matter and has, we can't just naively use the modular evolution. We write a code subspace of simple boundary operators acting on our state, U psi. It's a code subspace. And the criterion, I think, is that the modular flow preserves that subspace. And the idea is that that code subspace should contain the correct bulk operators acting on the state. It's basically because of the Bulk-Schleider theorem. The fact that in the bulk at the time t, acting with the operators near the boundary should be able to generate the whole Hilbert space of QFT excitations on top of that same background. However, scrambling tells us that the thing we will get by acting with the modular evolved operator, which is U conjugated, so the U by psi, is not the same as the bulk operator we wanted, phi U psi. And moreover, it's not the same as any simple operator A of t on U psi. So in other words, the left-hand side here is not just different from the right, but it's not even contained in the code subspace. So that's the conjecture. So if that's borne out, that will be a simple criterion to at least distinguish whether the reconstruction should work. So that's the story of that slide. And this one I'll put here, but I won't say aloud unless somebody asks me.
Okay, so I have a question actually. Is it meaningful to ask if the event horizon can be captured in this atmosphere algebra or not?
Do you mean the event horizon of a bigger black hole or of the probe black hole?
Well, that's, well, I don't know exactly. Maybe of the probe black hole, if it is sufficiently big enough to, I mean, to apply local gravity.
Yeah. We always imagine that's the case. But well, so I mean, the reason why I talked about this, maybe I didn't say this clearly. The reason why I talked about this atmosphere algebra was because the ultimate goal was to understand something about the bulk operators in the original spacetime without the probe black hole. So the probe black hole is supposed to be a tool to construct those operators. Therefore, the further away from the probe black hole we can construct correctly the bulk operator, the better, because that will be more similar to the correct operator that would act when you didn't have the probe black hole. Of course, you could try to discuss the operators that are very, very close to the probe black hole, and that's where the prescription kind of gets better. But those are, I mean, correct for the spacetime with the probe, but of course the back reaction of the probe there is strong by definition.
Well, my puzzle would be that it is sort of acausal, no? The behavior of the event horizon often. And from the perspective of any kind of local observer, it might not fit into some kind of unitary or I don't know. I mean, it looks a bit of a puzzle that it will fit into this atmosphere algebra, event horizon.
Well, maybe now perhaps now I understand what you meant. So the modular evolution itself acts approximately geometrically as a, let's say a boost relative to the extremal surface. So the extremal surface is some particular well-defined surface in the space-time between the probe and the system. It's not affected by things that later fall in that can shift the event horizon around, right? So that's what the modular evolution itself does. Since we wanted to discuss the atmosphere, which is defined relative to the event horizon, let's say the apparent horizon, then that is shifted relative to the extremal surface by things that later fall in. And that was exactly the point about these Shapiro delays, which are encoded by action of the maximal modular chaos exponent operators. So if I want to evolve my atmosphere and operators at fixed position relative to, let's say, the apparent horizon, that will not be the modular evolution, it will be the modular evolution shifted by those extra operators, which implement the relative shift between the motion relative to the extremal surface and motion relative to the apparent horizon. I didn't tell you how to compute whether the coefficient by which you should act with that operator, if you know the total evolution, if you know the correct answer, you can extract those coefficients. That's not very impressive, perhaps. If you can solve this frozen vacuum problem, then you will know when you need to act with those operators. So maybe is that what you're asking? I'm not trying to describe operators behind the horizon. Like, I'm not trying to describe operators sort of behind the horizon of the probe black hole, but I could try, but that wasn't my goal, I guess.
I see. Okay, maybe we could continue or take it on slide. I get some idea, of course. So maybe Shubho wants to extend the question, and that would be after this, we have to move on to the next talk. You want to extend your question?
Hi, Daniel. I didn't follow, every detail of the talk, but maybe you can tell me quickly if your construction, is it a perturbative in 1/n kind of a construction, or is it a fully non-perturbative construction? Because in that case, I will be able to probe the vicinity of the singularity as well, if your construction is non-perturbative in 1/n.
Right. Well, no. I mean, of course, the whole story here was in a way leaving order in n sorry, or perturbative in 1/n sorry. So in other words, the modular flow only acts geometrically in a certain approximation, which is limited by 1/n, as well as even more, by features of the state and so on. So, but if you worked non-perturbatively, then I will not. Of course, I can still discuss the modular evolution. It's well defined non-perturbatively. So maybe the point is it's well defined non-perturbatively, but it only looks like the geometric evolution at leading order, and in general, it will be more complicated or have some corrections that we may not understand. So, right. So for instance, in the case where you use this probe a probe of a two-sided black hole, if you continue the modular evolution of the operators, you can evolve them forever. And what happens after they will hit or get near the singularity is presumably, so the modular evolved operator is well defined, but you wouldn't know what's the bulk interpretation of this operator. Surely not evolving it past the singularity.
I see. Okay.
Or even in the vicinity of the singularity. Yeah, that's a good question. Thanks.
Thank you.
Okay, Daniel, thanks again for this great talk and very interesting talk. And
well, thank you.
Okay, so now it's time for the next speaker, Raghu.
Hi, I'm here.
Yeah, can you
I share my screen?
Yes, you should be able to do that because you're a co-host.
Could you make my iPad the co-host? There should be another Raghu.
There is no clone. There's a clone indeed.
Yeah, I think I got it now.
Mm-hmm.
Oh, sorry, not. One sec, just give me 1 second. Okay, I think you should be able to see the screen now. And
yes.
Okay, can you see?
Yeah,
Okay,
perfect.
Great. All right,
okay.
Yeah, I can start whenever.
Yeah, let's hear about entropy of Hawking radiation then from Raghu from Stanford University.
Okay, thanks a lot to the organizers for the invitation to speak. This will mostly be a review talk of stuff many people in the audience might already have heard several times, but hopefully it will be useful to the people who have not heard it or are hearing it for the first time. Okay, so this is going to be about deriving the page curve just from semi-classical gravity. And by semi-classical gravity, I mean GR plus some leading order quantum corrections from the matter. And okay, so just as a motivation introduction, sorry, this is not moving, I think. Oh, it is. There's a lag. Okay, I don't know.
Working fine. I think the lag is not so much a trouble.
Okay, good. So I just wanted to motivate this by saying the 2017 Nobel Prize, we know the black holes exist, they collide and send us these gravitational waves. And this year, we know that black holes exist and they also form under generic conditions. So I took these illustrations from the Nobel Prize website, and especially this figure on the very right is an adaptation from this paper, 1965 paper of Penrose. So we have this orange shell of collapsing matter, and it collapses and forms this black region, which is the inside of the black hole. The red line is the horizon, and the blue vertical line is the singularity. I sometimes like this picture in Eddington-Finkelstein coordinates more than the usual Penrose diagrams, because I think it gives some nice complementary information. So, but of course, the light does not travel on 45-degree lines, and therefore the light cones, which are shown in yellow and white, get tilted as you approach the singularity. And of course, once you enter the black region, there is no escape, and you have to hit the blue singularity. Okay, so, but the surprise, well, not surprise, this is an old result now. It's from Hawking in mid-1970s, is that black holes evaporate when we consider quantum fields on top of a black hole background. So here we have an extension of the previous figure where the dashed horizontal lines show some collapsing matter, and there's the black hole horizon which emerges, and maybe for a big black hole it will exist for a long, long time. But the point is that the horizon sort of shrinks. Like this line is shrinking slowly, and it will disappear at some point because of this phenomena of black hole evaporation. And inside this region, we have maybe, the thing we don't understand, and we would like to understand better eventually. And the singularity and the event horizon kind of merge near this endpoint. And we don't exactly know what happens here, but this is sort of the picture, that black hole forms, stays there for a while, and then the event horizon sort of shrinks and disappears. Okay, so this paper I just took directly from Hawking's paper. Anyway, so why does black hole evaporation occur? And again, these figures are from a review by Samir Mathur in 2008. So here, it's again in some Eddington-Finkelstein picture where we have these slices outside sort of, approach the constant R slices, and the time foliation would just be Schwarzschild. But of course, we know that in order to make the spatial slices go smoothly to the interior, we can't just take a constant R slice. We have to do something in the interior. So deep in the interior, we could maybe perhaps again have a constant R slice, but it needs to have this connector region to match up to this. So these are the so-called nice slices. And what's depicted on the left is that if you take a vacuum fluctuation, this could be one of the modes that enters into the expansion of a scalar field on a black hole background. And because this foliation is not an isometry in the space-time, this mode has some time evolution. And in these slices, the time evolution stretches these modes and leads to these C1 and B1 partners. So here you can see that the vacuum sort of stretches these modes, and you get these pairs. Okay, of course, these pictures are backed up by computations, and this is just meant to be an evocative picture of how these particles get produced. So if an observer is standing outside, he would see this perturbation B1 as a particle, as a Hawking particle, and C1 would be its partner behind the horizon, and B and C would actually be almost in a bell pair state. And on the right now, we consider two different modes. So this dotted there is this dotted mode here and a longer wavelength mode here. So the longer wavelength mode, of course, gets stretched first, and that is sort of the earlier Hawking radiation. And the wavelength, which is smaller, takes some more time to stretch, and that would be sort of the Hawking radiation that comes out later. So basically, this evaporation process leads to these pairs: B1 C1, B2 C2, and so on, like forever. Okay, and this is a problem because if the black hole eventually disappears and all you're left with are these B modes, then they would have an entropy which is the number of these modes times log 2. And that's a problem for unitarity because we should have the final entropy 0 if the initial entropy of the matter creating the state was 0. Okay, I just want to depict this in a different picture, which is taken from this recent review by Almeri et al. So the time here goes vertically downwards, and this each picture is a spatial slice from the previous picture, but rotated by 360 degrees. So in the first picture, maybe the black hole has just formed. This is the exterior region. The red line is the horizon, and we have an interior region, and there's some matter lying there. And what happens as you move forwards along these slices is that you get these blue squiggles, which are these B and C modes that I was showing before. So some of them are behind the red line, they're behind the horizon, and some of them are in the faraway region. And of course, this interior region, as you move the slices upwards, is getting very narrow because you're approaching the singularity in the future, and the radius is just the dimension of the transverse sphere, which is getting small. So eventually, near this point where the black hole completely evaporates, the interior is very, very small, and the horizon has become also very small. And eventually, we expect that the interior is just completely gone, and we are left with this gas of particles, these blue particles outside. Okay, so that's just a review of Hawking radiation and the information problem. Are there any questions at this point? Okay, doesn't seem so let me go on. Okay, so now about this page curve. The page curve dates back to 1993 from papers by Don Page, and ignore the curve that goes straight up, like it's constant for a while and straight up. Let's ignore that curve and just focus on the thing that goes up linearly and comes down. So on the horizontal axis, you can think of as time in the evaporation process. And what's plotted is the entanglement entropy of the B modes, of the B particles that were outside. So Hawking results might have led you to expect that you get in each sort of thermal time, you get a one particle, and the entropy goes up, 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 and it keeps going up like that. But of course, once you have more than half of the total particles outside, the entropy has to go down because it's a pure state, and the entropy of some system, some subsystem is equal to its complement. So this plot has to be left-right symmetric, and that is what Page derived by considering random states in a large dimensional Hilbert space. So that is why it's called here thermodynamic entropy, because right. So m times n in this language was the total dimension of the Hilbert space, and then what was plotted was as a function of the dimension of the subsystem. But in the black hole process, the dimension of the subsystem grows automatically because as time goes on, you're collecting more and more radiation. So the challenge, there's a strict challenge. There's an order 1 deviation. The Hawking curve would just have gone up, 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 but we need to predict this downward turn from gravity. And this is the puzzle. And you see, at this point, like let's say around this point, the black hole is not very small. It's still pretty big. So it doesn't have to do with the end of the evaporation process down here, where you say you might have lost all control and so on and so forth. Even getting this entropy to go down would be some sort of a success. So that has been the challenge, and well, we need to model this process somehow. And the point is, you might have thought that in ADS-CFT you could model evaporating black holes, but as we all know, big black holes in ADS do not evaporate. They are stable thermal equilibrium states in the boundary theory. So, and small black holes are, of course, not under boundary control. So this trick is, like Spenta talked about in his talk yesterday, is to take, let's say, an n equals 4 super Yang-Mills. Like, think of the field theory of n equal to 4 super Yang-Mills, and it's coupled to another system. Let's say there's an auxiliary heat path whose quantum dynamics we understand. It's maybe just even a free theory. And the purpose of this heat path is to wick away heat from this hot super Yang-Mills, degrees of freedom. Okay, so we will have some finite temperature super Yang-Mills coupled to a 0 temperature auxiliary system, and it's just supposed to wick away the heat. Well, but of course, it's easier to do computations in lower dimensions, so you replace the super Yang-Mills with a SYK kind of a model. So that's what's depicted here. Let's say at time less than 0, you have a thermal equilibrium state of an SYK, and you have this auxiliary system decoupled at time 0. This is a wire. So this blue line is supposed to represent some wire, which is this auxiliary system. And at time t equal to 0, you just join them. So this is now some excited state of the total system. The Hamiltonian, of course, is now H red plus H blue plus H coupling. So this will be a time-dependent state, which will evolve. And we don't necessarily have to think of a finite temperature state. We can just think of a high energy eigenstate, an energy eigenstate with a large energy. So everything is in a pure state. So anyway, so here we have it. We have our quantum system, which has a holographic dual, the SYK model. And then there's a heat path. It's a wire carrying a CFT2. So this is the setup that one can study. Okay, but I should warn you that, of course, the holographic dualities with such wires attached is not rigorously established, and it's conjectural what the gravitational picture is going to be. But I think that debate sort of goes back to Randall-Sundrum stuff, as maybe it will become clear later in the talk why I use the words Randall-Sundrum here. Okay, so here is the candidate dual description, and I think it's again taking some time to update the slide. Okay, here we go. Okay, so on the top figure, we have this SYK model, but we can sort of delete the red dot and replace it with this red line. So that is this emergent ADS direction, the radial direction in ADS. And maybe the hope is that in the holographic dual, this red region just smoothly joins on to the blue wire region. And of course, since we had a high energy eigenstate, there's a horizon, which I've shown deeper along the red line at the black dot. And the black region is supposed to be the region behind the horizon. And of course, the SYK system is not just gravity, it's the gravity plus the matter fields. And we assume for simplicity that the matter fields are the same on the blue side and the red side, and they can just freely propagate back and forth. So if you didn't have the blue wire, the matter fields in the ADS would be bouncing back. As they approach the boundary, you would have to put some kind of boundary condition. Now they just propagate out to the flat space region. And similarly, excitations from the flat space moving to the left can enter the ADS region. Okay, so technically you can model this lowest picture here as a ADS JT gravity plus a CFT, and the CFT fields propagate back and forth between the ADS2 and the wire regions. So what happens is that in this region we have the G mu nu and the phi, the dilaton, and the matter fields being dynamical, but on this side we just have the matter field entering the path integral. So, all right, so this is the model, and hopefully we can study it because it is ADS2. And okay, but our question, what was our question? The question was to compute some entropies, to compute some page curves. So, well, to compute an entropy, we need to say whose entropy do we compute, right? So our fundamental description, as I've emphasized, is this red dot plus the wire. And the claim, which is part of this, you can take it as a part of this holographic conjecture in the setting, is that the black hole should be this red dot plus maybe a little bit of the wire, right? That's what we call the black hole. And the rest of the wire is what we call the radiation, right? Because if you look at this figure, you can imagine the blue region is the far away asymptotic region if it was a flat space black hole, right? So there is some strongly curved region near the horizon, and far away we have flat space where the gravity is weak and so on and so forth. Okay, so that's it. So our subsystems will be defined by this split, the split of this black vertical dotted line. To the left, we have the black hole, and to the right, we have the radiation. And our task is to compute the entanglement wedge and entropy of the black hole subsystem, and also for the radiation subsystem. We just want to see which part of the bulk is dual to which part of the bound. Okay, so of course, just a quick review of RT and the quantum extremal surface formulas. This picture is taken from this nice review by Rangamani and Takiyanagi. So this region A here is a subregion on the boundary, the red A. And the point is about this whole business is that there is some substructure in ADS-CFT. It's not just the whole boundary is dual to the whole bulk, but the subregions are dual to subregions. And A is a subregion on the boundary, and we want to find its entropy and entanglement wedge. And the entanglement wedge is the piece of the bulk which is dual to the boundary. So this red region here between these two sort of wings will be the bulk region dual to the boundary region A. RT prescription told us earlier that we are supposed to find this blue region in the bulk, find a codimension 2 surface B. Sorry, I didn't label it here, but this is the surface B, a candidate surface B. And the restriction on B, it has to share its boundary with A, and there are some homology constraints. But okay, so it reduces it to a minimal area problem in ADS. And once you find that special B, that defines the entanglement wedge, like in this picture. And similarly for the complement. Okay, so one thing to notice is that the bulk Cauchy slice, which is a disk here, the union of that is equal to the full bulk. So if you split the boundary into two pieces, and the state is pure, then the bulk should also be, covered the same way. Like you have to cover the complete bulk if the state is pure. If the state is mixed, okay, then there are some subtleties, and we won't get into it. And this quantum extremal surface prescription due to Engelhardt and Wall is that instead of minimizing the area, you're supposed to minimize this other function L of B. So B is again some surface. And it's not just the area you're supposed to minimize, but it's the area plus the entropy of matter between B and A. So it would be the entropy of bulk matter in this region here, between the blue and the red. Okay, so it's a more complicated problem now, because as matter, we don't know in high dimensions how to compute it, etc. And if there are multiple extrema, then the correct surface is the one that minimizes SGen. This is going to be important, of course, because we will anticipate some phase transitions in this quantum extremal surface. Okay, so before I go on to the results, this is a good time to pause for some questions. If there are questions about the setup or what exactly is going on. Okay, so okay, so let's move on. So here are the results. Okay, I need to let this advance. Okay, here it is. And these are these papers from May by Pennington and Almheri, Engelhardt, Merolf, and Maxfield. The point is, before this page time, before this curve, was going up and going down, the entropy curve, at early times, when the Hawking result is correct, this quantum extremal surface basically lies close to the bifurcation surface of the black hole. Okay, and its entropy grows linearly in time, and there is no surprise. And But after the page time, after this halfway point in the evaporation, there is a different quantum extremal surfaces. There's a different quantum extremal surface whose generalized entropy is smaller. Okay, so you need to find the surface. You need to balance some gradients. So in S-Gen, we had two terms. There's the area and there's a matter term. And you need to take the derivatives and you need to balance the derivatives. And that leads to some cancellation of derivatives. And remarkably, there is this pink dot, which I have shown here. The pink dot becomes the correct quantum extremal surface at late times. It is located very close to the evaporating horizon. So this horizon, as time goes on, is of course shrinking. And because this surface lies so close to that horizon, its entropy is decreasing because its area is decreasing, right? So the fact that this quantum extremal surface is close to the evaporating, shrinking horizon basically gives you the page curve. The non-trivial part is canceling the derivatives there. And you can show that it happens. And I think the arguments are robust that a quantum extremal surface will exist. So once you found the surface, getting the page curve is almost automatic because it's just tracking the shrinking area, right? And this is very pleasing because one argument for the page curve going down is exactly the fact that the area of the black hole is becoming very, very small. So it should not be able to have that much entanglement, right? The entanglement of the stuff inside and the outside should be bounded by the area of the horizon. So I think these results very nicely capture this shrinking part of the page curve. And one thing just to emphasize is that this shows us that toy models like JT gravity are very valuable. And of course, we had a similar model in the 90s, the CGHS model. And indeed, these computations could have even been done there. And there was a very paper which was very ahead of its times by Fiola, Preskill, Strominger, and Trivedi, where they were trying to compute entropies of exactly such regions. But of course, this insight about minimization and trying to find, these special points in the bulk was missing, and because that came from ADS-CFT and the RT formula, which came later. But if somehow the RT formula or this extremization of the quantum extremal surface had been known at that time, then maybe it could have been discovered much earlier in the CGHS days. CGHS is basically flat space JT gravity plus matter. Okay, and on the right, I'm showing this. So sigma late is a Cauchy slice, and the Cauchy slice has to span both this flat space region and the black hole region. And what we are learning is that the entanglement wedge of this black hole, which was this red dot plus a little bit of the wire, is just a piece of the Cauchy slice. It's just this pink segment along the Cauchy slice. Okay, and in particular, this interior part is not in the entanglement wedge of what we called the black hole system, where of course the definition of the black hole system is this SYK dot plus a little bit of the wire. Okay, so the question becomes, if this purity in the holographic mapping has to be preserved and the entanglement wedge prescription makes any sense, then what should happen is that this, okay, now it should advance. Sorry, this is annoying. It takes a while to update the screen. Okay, this picture. So the region between YE and this bracket thing that I drew here, which was our bifurcation, was the entanglement wedge of the red dot plus a little bit of the wire. So the rest of it is just the entanglement wedge of the remaining piece of the wire, right? And this is just one of the consequences of purity. Like if you believe in this holographic description and you believe that pure states should reproduce the entire Cauchy slice in the bulk, then it means that the entanglement wedge of the radiation includes this piece which is deep in the interior of the black hole. And this looks very weird because you had a region which was very, very far away. It was just some non-gravitating region, and you might have expected that its entanglement wedge is equal to its causal wedge, right? So this is the causal wedge. The rectangle on the right is the causal wedge of that piece. And indeed, in the Fiola et al. Paper from the 90s, they only kept this piece of the entanglement wedge of the radiation. The surprise is actually the entanglement wedge is larger. It contains this piece on the inside. Okay, so it is just one of these extreme, maybe an extreme version of this familiar phenomena where the entanglement wedge is larger than the causal wedge. And the familiar setup there might be just two intervals in ADS3. In a vacuum ADS3, if you take two separated intervals, if they're big enough, the entanglement wedge is bigger than the causal wedge. And this is just one version of that phenomena where just the entanglement wedge consists of two disconnected pieces. And one of them happens to be on the inside of the black hole horizon. Okay, so concretely, one of the things it means is that we know that bulk reconstruction of operators that are in the entanglement wedge, but not in the causal wedge, are complicated, right? Maybe you have to do this modular flow, or you may have to do some PETSMAP or something. So it means that if you create a local bulk excitation in this island region, its description in terms of the wire is not going to be simple at all. And it's going to be some god-awful complicated operator, but supported in this piece of the wire which was far away. Okay, so all this is saying is that the boundary dual of this bulk operator that acts in the interior region, it belongs to the local algebra supported in the wire region, not on the SYK dot. Okay. So there is some kind of transfer of sharing, like who reproduces which part of the bulk as time goes on. So there is some rearrangement of the holographic dictionary as time goes on. Okay. All right. Are there questions about this?
Sorry, Raghu, one question.
Yes.
Can you go back? Like, can you explain this in terms of the original picture of like little waves that are stretching due to the tidal forces? Sorry, due to just the, not tidal forces, I meant just due to the spreading of the wave function.
Yeah, exactly. So that is my next slide. That's here. Okay, so here I have shown this spatial slice, and there were these particles which I have now drawn by these arrows. So the green arrow is supposed to be entangled with the green arrow behind the horizon. The yellow arrow is supposed to be entangled with the yellow arrow, and so on. So once you have gotten these two extremal surfaces, we can see how they compete. So let's say the surface one, which is just the causal wedge, is still a quantum extremal surface. It is extremizing the entropy. So it doesn't have an area cost because it is not in a gravitating region. It's just zero. So this zero means the area term, but it contributes to the bulk matter because you're only capturing one green, one yellow, and one brown. So that means that the generalized entropy is going to be 0 plus log 2 times the number of pairs in this far away region. And at late times in the evaporation, that's a big number. You have had a lot of evaporation. You have had a lot of particles in this radiation. The other surface, the surface 2, on the other hand, puts most of these partners in the blue surface. So now we pay a cost for the area because, you know, we put this point, we put the surface, this YE plus minus on the previous picture. Okay, so the price you pay is that you pick up some area term, but there is no more matter entropy contribution because both the green particles are now in the region whose entanglement you're computing. So these bell pairs that were being nucleated by the process no longer contribute to the matter entropy. So you see on the first surface, you have this term, and in the second surface, you have this term. And at late times, this is smaller. The area of the black hole is smaller than the amount of entanglement that has been set up. So that is why including this island is beneficial, because even though you pay the price of the area, you save a lot on this entanglement term. And that is exactly the kind of competition you need, which is why this generalized entropy quantity is very nice. Does that answer the question, Zohar?
Maybe it's a long discussion, but no, this is
Okay.
just automatic. I mean, you have some prescription which should give 0 at the end because the entropy of a pure state
Yes.
is 0. So it's just by construction going to come down, but I don't understand what's the microscopic mechanism. But it sounds like it's a long discussion, so maybe we should.
No, you're right that we don't have a bulk picture of how the information comes out or what's a more detailed mapping.
Yeah,
you should think of this.
I mean, what you're saying had to work like construction, sort of. So.
Yeah, but I would say that earlier people have said similar things, that the interior of the black hole should become part of the radiation. One concrete improvement is the fact that the point where you put the island is fixed. Like, there is it's the output of some computation. It is not strictly at the horizon. It is some definite distance behind the horizon. So what this extremizing this generalized entropy is giving you is it telling you like how much of the interior is being covered in this island. Okay, so that is a quantitative thing that, for example, researchers like Samir Mathur couldn't have said before, like how much of the interior is to be included. And of course, the intuitive expectations match up. Now, of course, we don't understand, for example, the singularity or anything like that, and I will have some comments after that. But what this is saying is that you do have a prescription of correctly computing trace rho log rho, even though you cannot compute rho ij. So if I and j are the matrix elements of the density matrix of the radiation far away, I can't tell you how to compute rho ij because I don't understand details of the singularity resolution and details of, how this interior piece that was getting pinched off, covers. But somehow what it's saying is that the trace rho log rho quantity is special, and there is this trick which you can use, and it gives you the right answer for that particular quantity, or even for trace rho squared and trace rho cubed and things like that.
May I interrupt and ask something, Raghu? Or you would like to take it?
Please. No, please ask.
So I have something related to Zohar. Whatever the mechanism is, which is making this speech curve work, how do we know that this mechanism is not violating causality, or do you think causality violation is fine even in the semi-classical limit?
Well, I should say causality is not being violated. Just like causality is not violated when the entanglement wedge is bigger than the causal wedge. You have some region which is space-like from your original region, and what you should say is that it's the union of these two blue rectangles which is encoded in some boundary region, right? So there is no loss of causality in this sense. It is not like I'm adding an operator which is coupling in the bulk these two regions or anything. This is just some statement about which regions in the bulk are dual to which regions on the boundary. And the only thing that could, if you create a local excitation here on the island region, and let's say you want to evolve it and see it appear on the outside, you can only do it using complicated operations like modular flow. And if you do those kind of operations, you can't trust the semi-classical geometry anyway, right? So there is no violation of causality. In fact, the positions of these quantum extremal surfaces obey these kind of quantum focusing conjectures and things like that, which actually protect causality on the boundary, like causality in the boundary sense. Like you cannot, if you define causality using the boundary, this red dot, this SYK dot union the wire, and who can send signals to whom, there is no violation. That is where the causality should be defined, because that is the fundamental description, and that is where the local algebras have their definition. The bulk picture is just some perturbative statement about some state, and the picture captures some things and doesn't capture other things. But the fundamental description is really this purely quantum mechanical description.
Thank you.
So for example, in our, I hope those comments were a little bit clarifying, but we can discuss more later. Or
Sure.
Yeah, so it's definitely not a solution, I wouldn't say this is a solution to the information problem, or it is the final word on this body of research. It is just that we learned how to compute one more piece. We learned how to compute this downward curve, but we don't know, for example, how to compute the actual final state of the radiation, like the S matrix, for example, from in to out, we don't know how to compute it. And we don't know rho ij for each I and each j. We don't know those matrix elements. So there's definitely more work needed here. Okay. All right, so now just to say that these islands are sort of robust is you can even have these islands in just static geometries. So we discussed this in a paper with Almheri and Maldacena from October. So, so in this top figure, you just have 0 temperature ADS2. It's a Poincare patch of ADS2, and it's coupled to a wire. So this is the wire region, and on the side, I have shown the dual description. And let's say the joint system is in the 0 temperature ground state, coupled system in the 0 temperature ground state together. And what you find again is that this the SYK dot plus this green region, only the entanglement wedge is not all of the Poincare patch. It only goes up to this point minus A in the bulk. So it's not all the way to the Poincare horizon. So again, it is showing you that the entanglement wedge of this wire piece, which naively you might have thought would just be its causal wedge, actually includes an island deep in the interior. So this is a very simple example, and even the entropy function that you minimize here is something like 1 over x plus log x. It is as simple as that, and this function has a minimum for some x, right? Like it's just the derivative vanishes at some point. So that's basically the idea. Okay, so it's a very simple example, and if you soup the first figure up a little bit. Soup up this figure a bit to go to finite temperature situation. So now just imagine this SYK plus wire being in the thermofield double state with a partner exactly like this on the other side. So we have 2 SYK dots, each respectively coupled to their wires. The left SYK plus wire being in a finite temperature state, the whole thing being in a pure state. Then you get a picture, sorry, like this. So this is the ADS2 region demarcated by these vertical lines, and it's glued onto 2 flat space regions, right? And what we do is consider this state. So you start with the thermofield double state, and you apply time evolution using h left plus h right, not with a minus. The minus would keep the state invariant. So having this plus sign is important. And this is a genuine time-dependent state, for example, emphasized by Hartman and Maldacena. And this setup, and in this setup, what we want to compute is the entropy of this blue radiation region union its partner on the other side. So for people who are familiar with Hartman Maldacena, this would sound familiar. Like you pick some subsystem on the left, union its mirror subsystem on the right, and you ask for its entanglement entropy as a function of time. And what they found was that, of course, it grows linearly in time initially because it's a quenched state. This is a time-dependent state. And the thermofield double with respect to the Hamiltonian h left plus h right is just some highly excited state. So indeed, you get a linearly growing piece. But we know the entropy can't increase linearly forever because the complement is 2 SYKs. And the SYKs have bounded entropy. So again, there has to be some kind of cutoff in the linearly growing piece. And indeed, at late times, you get the picture on the right, where the entanglement wedge of the blue, the left blue union the right blue contains this island, which spans the black hole interior, and it has these endpoints here. So what we say is that the left blue radiation region, the right blue radiation region, union this island is together one local algebra. Right? That is the statement, that is the thing that defines local algebras in gravity. And if you compute entropy of that, you get a constant at late times. So you reproduce this kind of page curve even in this setup. Okay, and I should say that this version of the information paradox was discussed by Samir Mathur in this paper from 2014, where he was discussing forward time evolutions of the thermofield double states. Okay, so this is just saying that these islands exist in other scenarios as well, and they play a similar role in avoiding these entropy paradoxes. Okay, questions? Yes.
Yeah, can we finish in like few minutes so that we can take more questions?
Yes, sure. So I just wanted to say that this is maybe important, like, you know, we have these blue regions that sort of now consist of this piece plus a disconnected piece in the interior. And this might seem weird. And in the May papers, it was not exactly clear that this purity is being preserved, like the black hole union, the radiation is equal to the whole system. But if you assume that this matter CFT2 is itself holographic, so it nucleates a third direction. So the direction this way is Z. So I'm not showing time. There is no time. This is the boundary space. This is the bulk, the 3D time. The entanglement wedge from the 3D perspective is just connected. Okay, so this sigma naught to infinity was the radiation region. YE to the inside was the island. And what happens is this entanglement wedge sort of comes out of the radiation region, out of the plane of the previous figures, and attaches itself on the island. And so this is a justification that this is just some kind of usual entanglement wedge. And that is why I was using the words Randall-Sundrum, because we have this Planck brane here. So this is the brane on which this JT gravity lives. And it's matched on to just an ADS boundary infinitely far away, which is this flat space region, which does not have gravity. And the nice thing also is that once you have this one additional dimension, the bulk entropy piece also gets geometrized. So you might have thought if you are doing this in ADS4, S matter is impossible to compute. But if that S matter is itself the entropy of some holographic system, that would just be computed by some area in this Randall-Sundrum gravity. And that is indeed correct, and it simplifies life. So you can consider generalized entropies very easily in this Randall-Sundrum kind of scenarios. And anyway, the point of the next slide was going to be that this allows you to do computations in higher dimensions. So if you do this eternal Randall-Sundrum doubly holographic setup, you can add 2 dimensions to everything I've been saying so far. So right now it was SYK plus wire, just add 2 spatial dimensions to everything. And George Santos, being him, it's trivial for him to solve 5 PDEs of like 2 variables and fill in the geometry numerically and find the minimal surfaces numerically. And indeed, you see some similar island phenomena. So since I'm short of time, maybe I'll just wrap up to say that there is.
How much time you need more, Raghu?
Just a couple of minutes, I think.
Oh, sure. Okay. No, you can take a few more, maybe 3-4 minutes. We can finish.
Yeah. So I just want to say that just looking under the hood of where this island comes from is the entropies are computed using trace maybe rho squared or trace rho cube and analytically continuing in this index. And if you do the Levkovitz-Maldacena setup, so you try to set up the boundary replica trick, okay, and ask for the answer to trace rho squared by filling in all possible bulk geometries, what you find are these novel geometries that connect the different sheets. And what happens is that there are some additional ZN symmetric points that are emergent. So in this lower figure here, this red stuff, these red dots are supposed to be additional fixed points of the ZN symmetry of the replica manifolds. And what these lead to are some emergent twist operators. So you're not just computing the entropy of these 2 cuts on the boundary side, but you have these emergent twist operators in the gravitational region, and you end up computing a 4-point function of twist operators. And in the n goes to 1 limit, it's the location of these twist operators that becomes the location of the island. Okay, so there is some story with these disconnected geometries and so on, and this was in these 2 papers from November, one by the group at Stanford and one by the group at Cornell and IAS. Okay, anyway, so the point is this islands have an image in the higher replica, the higher Renyi entropies as well. And again, like you pay a cost to nucleate these twist operators, but you're saved by the fact that the correlation function itself is going to be smaller. Anyway, so this is some of the things I already said in response to the question from Zohar. So, okay, why is this not appearing? Okay, so I think I like this quote by Witten from '91 when he was working on this two-dimensional black hole in string theory, is that if cosmic censorship, for example, was false, then in principle, we would have the chance to observe new laws of physics at the would-be naked singularity, right? So a horizon is kind of a pain from that point of view because we can't access the singularity easily. And one might have hoped that an explanation of the page curve would require somehow some information about how black hole singularities are resolved, right? That might have been the hope up to like a few years ago, that, okay, we don't know what's going on near the singularity, and maybe to get this downward slope, you need to resolve the singularity somehow. But, okay, let's go. I don't know what, okay. But what I said is that semi-classical gravity seems to be really smart in computing certain quantities, like trace rho to the n or trace rho log rho. And the only input from the UV structure seems to be the finiteness of this generalized entropy quantity. Like this is this usual story that the renormalization of G Newton is supposed to cancel the UV divergences in the matter entropy. But other than that, like, it's just GR plus matter. And the lesson we should just take away is that these special quantities are just special. And we didn't need to know all this extra stuff. Okay, the dream question is semi-classical gravity smart enough to also know about all of the matrix elements rho ij, which is the same as knowing the precise state of the quantum radiation. And my guess is that it's unlikely. You probably need to know what is happening near the singularity in order to get the precise final state of the radiation from the bulk point of view. Okay, and then just my final slide is what's the future? The future directions are what Dan already talked about. One thing I think is very important to understand infalling observers, and also maybe applications to de Sitter space. And for that, I would highlight this recent paper of Chen, Gorbenko, and Malvasena. Okay, thanks for listening.
Thanks for this amazing talk, Raghu. And so we should take questions now.
Yeah, happy to.
I have a question, Raghu.
Yes, Penta.
What would be the signature of the black hole singularity in the boundary gauge theory at large end? What would you be computing to see it?
Yeah, it's a good question. I was asking you this question yesterday, and you're asking. The short answer is I don't know. I can say one thing, which I think is interesting. Like, let's imagine a simpler singularity in the bulk. So let me just remove this thing, which is, let's ask about the bulk point singularity. So we know that if you're just computing some 4-point function, you know, in the boundary theory, it can have some singularities in holographic theories that are not there in a finite NCFT, like this bulk point singularity, where two particles come in, they collide at some point in the bulk and go out. Like, we can ask, what is it about the CFT data at strictly infinite n that is causing this fake singularity? And I think the answer there is sort of understood by this HPPS mechanism, that the structure of the anomalous dimensions is very special. So the gammas of the operators is very special, and that sort of conspires to give this weird singularity in the 4-point function. So you need some things like that CFTs at strictly infinite n have to have some special properties which lead to these kind of singularities. Of course, they are all resolved at finite n, but I think it's an interesting question to ask. Is there like a strictly infinite n kind of a bootstrap that sort of tells us about these singularities? And, you know, like saturation of these chaos bounds and this bulk point singularities are sort of minor examples of this. Of course, the black hole singularity is much more severe. It affects all observables. Basically, yes, a lot more observables are getting affected by the singularity. So maybe there is something about the operator data, maybe of some high dimension operators, not just point-like operators, but lines and branes and whatnot, that would tell us that at strictly infinite end, the singularity has to be there. But yeah, beyond that, I don't have any smart things to say.
Yeah. Thank you. Thank you.
Yeah.
Thanks.
There's a question from Tushar Gopalka, but Tushar apparently doesn't want to ask it himself. Should I read it out for you, Tushar?
Yeah, sure, please. I can also read it.
Okay, so the question is that there was an early 2020 paper by Verlinde in which he argues that for a two-sided eternal ADS black hole, the entangled boundary degrees of freedom cannot completely decohere, since classical correlations are topologically protected. Does that work modify the end result from the island story in some way?
I think you're referring to this paper that had the thermomix double state, right? That talked about this thermomix double state. Okay.
He says yes.
I think that's an interesting state, but it is not the state that is being considered in these evaporating setups. So it would be interesting to find what is the bulk dual of the state that Herman is considering, but I don't think the conclusions of that paper apply to these setups. I think that's one thing I can say. But it's an interesting state that he wrote down, and I think it would be fun to figure out what its bulk dual is. I don't think it's this. It's the evaporating black hole. That's the answer.
Okay, he's satisfied.
Okay.
So any more question? Okay, I hope people will continue on Slack though. I mean, please join Slack and we can keep engaging there. So we should go to our next talk.
Okay, thanks a lot.
Thanks, Raghu. Thanks a lot. Thanks again for this marvelous talk. So our next speaker is Samir Murthy. Samir, you are already the co-host.
So should I start sharing the screen?
Yeah, you should be able to share the screen because you're co-host.
Let me just check. There we go. Share. There, do you see it?
Yes, it's fine. It's perfect.
Yeah. So tell me when I should start.
Yes, so we should start now. So our next speaker will be Samir, and we will hear from him about 116 BPS index and supersymmetric phases in 4T n is equal to 4 superangles.
Okay, thank you very much. Thank you for the invitation and the wonderful organization of this workshop. I've been trying to catch as much as possible. In fact, I visited the beautiful campus of IIT Madras many years ago when I was a student in IIT Bombay myself. Hopefully we'll all be able to meet there physically, but for the moment, it's a pleasure to give this online seminar. It's an honor to be invited here. My title is the 116th BPS index and supersymmetric phases in n equal to 4 super Youngman's theory. So the first half of the talk, the next 20 minutes, I just want to explain the various parts of the title, rather remind you all of the various parts of the title. I'm sure all of you know most of it, and try to set up the main question that I'll be addressing. And in the second half of the talk, I'll tell you about progress in answering this question. But before that, I want to start by maybe some broader orientation. So there's a long-standing idea in our field that QCD or gauge theory in the limit when the number of colors becomes very large, n, is secretly a string theory, going back to the work of 't Hooft and others. And the evidence for this is this theoretical evidence like the 't Hooft diagram expansion or the loop equations and so on, or also evidence coming from phenomenology, Rajay curves, or looking at lattice, so flux tubes on the lattice and so on. And I think it's fair to say that these diagrams, by the way, can you see my pointer?
Yes. Yeah, it's Yeah, as long as it's not within the box, we can see it.
Oh, so wait a second. There's a way to do this on Zoom. I forgot how to do it.
You can choose this more option. You can get annotate, and then that will be a spotlight option if you could.
Thank you very much. Yeah, so I'll use that. Okay, now it's visible, right?
Yes, yes.
Okay, great. Okay, so oops, I killed it. Sorry about that. Okay, so I think it's fair to say that by now, I don't know how to get rid of this thing.
We can't see it anyway.
Oh, perfect. Okay, great. There's a bar which appears on my screen. Okay, that these pictures by now have, I think, embedded themselves in our collective scientific imagination. So this is the electromagnetic field where the field lines run away to infinity. And here you see the quark, anti-quark field lines, the strong force, where you see the flux tubes or the strings. Right? It's the influence of the work of David Gross on all these ideas is very well known and doesn't, I don't need to repeat any of that. What is slightly less known, apart from the experts, is a more direct theoretical identification of the string theory. So the context is two-dimensional Yang-Mills theory, and these authors showed that, let me get rid of this now. These authors showed that that all observables of two-dimensional Yang-Mills theory on any Riemann surface can be recast as a sum over partitions of the integer n, the rank, with a weight which can be identified as the action of a certain string. Okay, so people sometimes call this the Gross-Taylor string. So that's another part of the story. And a more modern sort of answer to this question is, yes, indeed, larger gauge theory is a string theory, but a different type of string theory. Namely, it lives in anti-de Sitter space in one dimension higher, and it's a gravitational theory. Okay, and in particular, the string excitations are only part of the spectrum of this theory, and it also contains non-perturbative excitations like black holes. Okay, so one question to ask is whether these two string descriptions of the large N-gauge theory have anything to do with each other. Okay, this has been asked before, and I'm not going to have a definitive answer. But towards the end of my talk, I want to present some hints that indeed there may be some relations between these two string descriptions. Okay, so the rest of my talk will be much more concrete, and I want to talk about a sharp puzzle that has been around for the last 15 years or so in the context of ADS-CFT and black holes. And in fact, it's the original prototype ADS-CFT correspondence. So you consider n equal to 4 super Yang-Mills theory with UN gauge group on a 3-sphere. The holographic dual of this is a gravitational theory on ADS 5 times S5, whose conformal boundary is the same 3-sphere. Here I've sort of cut the ADS 5 to show you the interior. And this theory has black hole excitations. And in particular, there are black holes which preserve 2 of the 32 supercharges of the theory. Okay, so these are 116 BPS. And these black holes are large in the sense that the area of the event horizon in Planck units, when translated to the field theory units, grows as n square, where n is the rank of the gauge. Okay. And the main question is, can we account for the thermodynamic entropy of this black hole, which is over here, as a statistical entropy? Okay. And the natural place to look is 1/16 BPS states in the Yang-Mills theory, in the dual Yang-Mills theory. And this function here, called the superconformal index, it's like a partition, it's a supersymmetric partition function, which gets contributions from these states. So in effect, it counts these 1/16 BPS states like a Witten index, trace minus 1 to the f, with certain chemical potentials tau I turned on for certain charges qi. I'll be more precise about this as we go along. Okay, so this is like the partition function. So the question is, does the free energy of the theory also see this n square scaling? Right. So this question was posed in these papers, and And that led to a lot of work on this question since then. And at that time, it looked like the answer to this question is negative. Okay? And over the years, there's been a lot of work on this problem. And recently, in the last few years, people have been revisiting this problem. And now it looks like that the answer is yes. Indeed, there's an n-square scaling to the free energy. And in fact, not just that, you can actually capture precisely the black hole entropy on the nose, including all numerical factors at large n. Okay, so this is what I want to tell you about. But in the introductory part of the talk, I want to first tell you about the various objects. So the index, what is this index here? What are the black holes? And what is this expectation that these two are equal? I just want to spell out the details to put everybody on the same page. Okay. So any questions so far about what I said or what I want to do? I'd really prefer it if you interrupt with questions in the beginning rather than keep them to the end. So I'll just wait for it. Okay, very good. So before going on, I should say that this question is not unique to n equal to 4 super Yang-Mills theory. Exactly the same question can be asked in any n equal to 1 super conformed field theory in 4 dimensions, which has some kind of a large n dual. And the only difference in the slide between the previous one is the fact that I've replaced 1/16 by 1/4. So here the theory has 8 supercharges. So the black holes and the states are 1/4 BPS. And the question remains the same. There's this index function. And does the free energy grow account for black holes? So let me first tell you what this index is. So consider a generic. So I'm going to use this more general language also because it's easier. So consider generic n equal to 1 super conformed field theory on S3. So there are two angular momenta on S3. And the n equal to 1 super conformed algebra has a U1 R charge called Q. So states have these three quantum numbers Q, J1, and J2, and as well as energy. And supersymmetric states means that you consider a complex supercharged curly Q with this algebra QQ bar. Anticommutator is this right-hand side. E here is the energy. Now, if you want to look at the index of Q, the subspace of states annihilated by Q, then you should ask what are the charges which commute with the supercharge. And of these three charges, J1, J2, and Q, there are two combinations, J1 plus half Q and J2 plus half Q, which commute with the supercharge. And if the states are supersymmetric, then E will be determined by the vanishing of the right-hand side. Okay, so the most general index is like this. It's trace of -1 to the f, e to the minus beta QQ bar, times the coupling to these conserved charges, commuting charges, J1 plus half Q and J2 plus half Q, to chemical potentials, which I'll call sigma and tau. Okay. Now, of course, we all know that this index doesn't depend on beta because of the usual pairing argument. So I won't write it from now on. And I'll also, for this talk, consider the simpler situation where sigma equals tau. Okay, that's just to make the presentation easier. So there's one combination of charges, 2J plus Q, which labels the BPS states. Okay, so everything I say, by the way, can be generalized to, I mean, equal to 4 super Yang-Mills. You can also sort of dress it up further by keeping track of additional global symmetries and so on. I won't discuss this here. It's in the paper, or you can ask me questions. So this here is the sort of simplest, most general index, which captures the 1/4 BPS states. And now you can look at a Fourier expansion of this index. And these Fourier coefficients, D of n here labels this charge combination. D of n should be thought of as the degeneracy, of course, with its bosons minus fermions type of object. Okay, so one can go between this micro-canonical ensemble or the canonical ensemble. So D of n or I of tau, and it's useful to go back and forth sometimes. So if there's a confusion, I'll call this the index, and I'll call this the index function. Sorry, Ian, can you hear me?
Yeah, there was some
problem
with the audio, but you're back.
All right. So I use a factor, normalization factor here, which comes from, I've taken the n equal to 4 normalization, where the R charges are quantized in units of 1/3. So that's as far as the index is concerned.
Samir, one question here.
Yes.
Can you remind us that for ADS black hole, J1 and J2 can be independently varied, keeping supersymmetry, or what is the story?
Yeah, so that's exactly my next slide. So this is, thanks Amitabh. So this is the index, the field theory side. And now let me tell you about the black holes. And if I don't answer this, please ask me again. So what are the black holes? So you look at minimal 5-dimensional supergravity. That's the context in which actually these black hole solutions were first found. These have 8 supercharges. And the black holes preserve 2, and they carry 3 charges, J1, J2, and Q. And it's actually useful to scale out the Newton's constant and talk about some gravitational charges, small J1, J2, and Q. Now, the simplest solution you can take when J1 equals J2, so the black holes are rotating in one plane. This was the first solution by Gutovsky and Rial that was found. So now you have 2 charges, J and Q, but in fact, they're not independent. If you look at the black hole solution, you realize that J and Q obey a certain nonlinear relation. Okay, so here I've shown you the graph. It's explicitly known. At large charges, the relation goes as J square equals 2 times QQ. Okay. This relation is slightly complicated, and I think this was one of the reasons why this problem turned out to be a little bit thorny in the beginning. Okay. And now you can measure, so basically now this means that you can label the black hole by 1 charge J. And so the entropy is n squared times a certain function small s of J. Okay. So this is sort of the simplest situation in which the puzzle is sharply defined. The entropy of the black hole is 1 function of 1 variable, and the microscopic statistical degeneracy is also 1 function of 1 variable. Okay, now we want to compare the two. So Amitabh, did I answer your question?
I guess more general black holes are, so maintaining supersymmetry, more general black holes are there with J1 not equal to J2. If there.
Yes, yes. So this is the simplest situation I'll discuss, but everything I say can be generalized to all those more general black holes. Yes.
Yeah. Okay. Thanks.
Sure. Okay. So the main point is that a priori there are some number of charges, but there's one relation which reduces the number of charges, which is nonlinear in gravity. And from field theory, that comes from just this looking at the commutant of the supercharge, which automatically reduces the number of charges that you can have. All right. So now the question is: do the microscopic and the thermodynamic entropy, do they agree asymptotically? Right. So let me show you what this entropy is. So here is a plot of the entropy versus the charge n. And you see, for large charges, the entropy goes as 2/3, n to the 2/3, or j to the 2/3. And that you see in the horizontal shape of the curves. And here I've also shown you the growth with respect to the rank, n square growth, if you go in this direction. Okay. For reference, I've shown you the entropy of the index of a multi-graviton, of a gas of gravitons carrying the same charge, which is very, very small. Okay. And now I just want to clarify what people mean by this kind of, this is supposed to be an asymptotic limit. There are 2 limits which people discuss. One is the so-called, one is what we always call the large n limit, the usual large n limit. But what it means in this context is that you should keep the gravitational charge fixed and scale n to infinity, the rank to infinity. That's the regime in which black hole solutions are usually described. Supergravity is described, and J is some order 1 number, let's say. You can also have a Cardy-like limit. Cardy-like because you fix the rank n or the central charge, and then you just scale the charge to infinity. Okay. So this is, if you want, what this means is that it could be that the sort of how to say, the curvatures are large, but the black hole is very, very big and fills up the ADS space. That's one way of thinking about it. Okay, these two are a priori completely different limits. There's a regime of overlap when both the gravitational charge and the rank go to infinity. Okay. So you can start there and then move towards smaller rank. Any questions about this?
Yeah, Samir, I have a question.
Yes, please.
Yeah. So you have these two quantities which are related, n and j, right? You showed in the black hole side.
Yes. J and Q. Yeah.
J and Q. Yeah. What about on the microscopic side?
So microscopic side. So remember, so let's say there are 3 charges here, but only 2 are independent.
Yeah.
Right. In the microscopic side, there are also 3 charges, but only 2 of them commute with the supercharge. So the index can only be defined with respect to 2 charges.
Okay, but does it matter which 2 charges you pick when you compare? Because there is a relation between J and Q, right? So you could have picked either Q or J. I mean, keep that fixed and then compare the.
Yeah. So that see, the thing is that large charges, one of them dominates.
Okay.
So that's why I picked J. So at large, so what I'm saying is N, this combination N, which is 2J plus Q, for very large charges is just J.
Okay.
So what I'm saying is what you should really compare is N. So you can do that. So what you can do, as you'll see later, that in the field theory, you calculate dn of n, and this will be compared to the black hole entropy as a function of n. I mean, here I've called it J, but it's really n once you sort of take this relation into account.
I see.
For large charges, you don't see the difference.
But if you had used Q as the independent variable.
Yeah, that Q then is not equal to this n here. Sorry for going back and forth. It's not equal to n at large charges, because for very large charges in gravity, it's J that dominates.
Okay.
You can do that. You'll just have to do some change of variables. You can choose either of them for to compare, but then n is not equal to Q anymore.
I see. Okay. Okay. Thank you.
All right. Any other questions? Okay. Now it's actually useful to recast this question in the canonical ensemble. So this question of whether the microcanonical entropy equals the area of the horizon is the same as asking whether the free energy asymptotically equals a certain function. This function is just a Legendre transform of this function. Okay, I've just done that for you. And S is a slightly complicated function, while the Legendre transform is something very simple. Okay, you can ask what's the meaning of this in gravity. I'll tell you in a second. Before that, let me say that the 2 limits that I discussed have analogs for the canonical partition function. So the Cardi-like limit is just fixed rank and take tau to 0, and the larger limit is fixed tau and take n to infinity. Okay. So this is actually an important part of the story, at least for me, but I'm not going to do it here. I just want to say that the meaning is exactly what you would think it is, namely you take ADS 5, and of course you're looking at Euclidean solutions. So this free energy is literally the free energy of the ADS 5 black hole solution with ADS 5 asymptotics. So what you do is you take the supersymmetric black hole, you regularize it a little bit, you weak rotate it, and then embed that in, look at the full ADS 5 asymptotics, and you'll get some cigar-like geometry. And this free energy is just the action of that geometry, regularized action of that geometry. Okay. All right. So now the only thing I haven't told you yet to set up the problem is what is this index function? This index function has been known for a long time. It's an integral over UN matrices, okay, whose potential is governed. It's an infinite set of terms, and it's governed completely, by one function called the single letter index. This single letter index is the same trace that I showed you in the field theory, minus 1 to the f times e to the 2 pi I and tau, but on the space of single letters of the theory. Letters just means you take f mu nu, or the various fields of the theory, f mu nu, or the fermions, or the scalars, and so on. And then what you do is you evaluate it at one point. So let's say the origin. So that's some quantum mechanical space. So those are the letters. So this is easy to calculate. And then what this exponential does is to So put the letters together into words of the gauge theory. So these are sort of all operators. And finally, the integral projects you onto the gauge invariant space, space of gauge invariant operators. Okay? So that's one way to understand this formula. You can also derive this using path integral methods using localization. All right. Now, there are two things I want to say about this formula. One is that this pure double trace so there is no single trace in the exponent, only double trace. That means that in terms of the eigenvalues, there's only a two-particle interaction. And secondly, if you think of the coupling constant of the theory, that's set by tau actually. Tau is intrinsically a complex parameter, and so the coupling constants are complex. Okay, so this is to be contrasted with, let's say, the Gross-Witten-Wadia model. Okay, both these points will come back, and these are important parts. Okay. So in the last couple of years, there's been a lot of activity, and what I want to tell you is based on these papers. I won't cover all of these papers. What I'll do today is focus on two main questions. Firstly, can you understand the black holes as some saddle points of the matrix model? Okay, and the answer is yes, and we can do that using some interesting relations to functions coming from number theory. And if you can do that, one natural question is, are there other phases, and what are the interpretations? So that's one question I want to answer. The other question is, so there's this law that gauge invariant supersymmetric operators in the theory correspond to multi-graviton states. That seems to be in conflict with the fact that the matrix model also contains black holes. And how do you resolve this tension? And here's where there's a nice way of understanding this in the language that I referred to in the first slide, namely as a sum over random partitions, as some effective string theory. I have not identified what that is, but that will be useful. Okay, so this is what I plan to do in the next 20 minutes. Any questions so far? Okay, so then let me continue. So first, let me show you some data. So here what I've done is to just plot the log of the degeneracy, absolute value of the degeneracy, so I'll call it entropy, versus the charge n. And the dots are the Yang-Mills values, and the solid lines are is the prediction from gravity. The solid line is just the black hole entropy. The dots are the Yang-Mills values. And I've just plotted it for n equal to 2, 3, up to 10. Right? So there are three things you can see from this from these graphs. One is that, well, the most striking thing, of course, is that the Yang-Mills values follow the prediction very, very closely. Okay, so this already should be quite convincing that the model does have growth of black holes. The second thing, you can see it most clearly at large values of n, is that there's an oscillation. There's a periodic oscillation. This I don't want to spend time on the talk, but if there are questions later, I'll explain how that comes about. And finally, again, you can see it most clearly at large values of n. Before the curve latches on to these oscillations, there's a bit of a gap where it does something funny. Okay, so for small charges, it looks different. Then there's some continuous oscillations which go around the gravity prediction. Okay, so that I'll come to towards the end of the talk. So first, I want to now explain the growth, and then I'll tell you about the low
Quick
charge.
question.
Right?
Quick question.
Yes,
In all of them, there are a few points that are kind of very far from the curve.
Yeah, like this one. Yes.
Yeah, like this one. Is this understood?
Yeah. So this is not. So I can. So I think I understand them, and I can explain this. Yeah. So I think let me tell you briefly what the answer is, and then I'll tell you later in more detail if you want. So briefly, what I can do is. So let me tell you the experiment first. So the experiment is I take the Yang-Mills theory, I divide by this prediction, so I get something more horizontal, and I see the oscillations. Okay. Then I have to do some something to if you do that naively, you'll see some mess. Okay, so you have to do something to see some clear oscillations, and you can sort of recast the data in a way that there's really just a cosine curve in certain variables. It's just a choice of variables. So the answer is yes. Now, the main question there is, why is there an oscillation at all? And the answer is that, in fact, there are two saddle points which are competing, which have the same entropy, but different phases, okay, which are exactly the same entropy at large n. And that explains all of these oscillations, including these points.
Thank you.
Please ask me later if that was not satisfying or anything. Okay, let me then continue. So now let me tell you how to analyze this matrix model. So the first thing to do is the usual thing. You take this unitary matrix and write it in terms of the eigenvalues. The eigenvalues live on a circle. And I'm going to, the variable, nice variable is u, the phase. So I'm going to call this eigenphase, which goes between 0 and 1. It's periodically identified. So when you take this Haar measure and write it in terms of the flat measure, oops, over here, there's this van der Monde type object. That's a two-particle interaction. Everything here is also two-particle. So what you get is some action of the eigenvalues, which is purely two-particle. Now, if this u goes between 0 and 1, and there's a pure two-particle interaction, let's say it's a repulsion, then the only sensible saddle point I can think of is when they're all uniformly distributed. Okay, it's a circle. There is also a saddle point where all of them actually clump up at one point. That's singular, and the index actually vanishes at that point. So I'm going to ignore that. Sorry, I should have said something obvious. The fact is that there are n squared terms in this action, so you can scale out an n square, and that's why I can use a saddle point approximation at large n. I think this everybody understands. So you have a uniform distribution between 0 and 1, and if you calculate the action of this distribution, you get 0. Okay, this was done in the original papers, and so now we want to somehow get around that. How to get around that? Well, as I said, this issue, the fact that the coupling constant is also complex is important. So let me just expand on that a bit. So tau here naturally lives on the upper half plane. So tau, from the field theory point of view, tau is just some external gauge field. Okay, and if you write it as a series, you have q is e to the 2 pi at tau. So tau is some complex object. But in fact, from the real hint comes from gravity. So this was in our 2018 paper. If you just track what is tau in gravity, it's some chemical potential. But on the solution of the black hole, this regularized Euclidean solution that I discussed, that I just mentioned, you can ask what's the saddle point value of tau, and that is complex. Okay, so that's a hint that you should look at complex values of tau. It's sort of, you're restricting yourself too much if you look at only real values of tau. Okay, there are other simpler ways of understanding it from the field theory. If you think of q is e to the 2 pi tau, you write I of tau as some d of n q to the n. And you ask for a saddle point value of d of n. You should just scan over all the saddle point can have a complex value. Okay. So now, if the coupling is constant, then it's sort of a natural guess that the fields themselves should be allowed to be complex. The U fields should be allowed to be complex. And that's what we did. So here is, this is the 0, 1, the original contour of the model. Here is tau. And what I'll do now is to extend the potential of the model away from this real line to the whole complex plane in a way that is periodic with tau. Okay, so there are two periodicities, 1 and tau. In other words, there's a lattice, okay, or a torus. And the story is that every cycle of the torus or every lattice point gives rise to a saddle point. Okay, so there's an infinite family of saddles labeled by lattice points. This GCD condition just makes sure that you don't overcount. And now you can calculate the action, and it turns out that the A cycle is just has entropy equal to the entropy of P radius, and the B cycle has entropy which is exactly equal to the entropy of the black hole that we're after. Okay. So now I want to explain a bit of details of this story, unless there are questions. Okay. So,
if I may, so you have a lot of saddles. You said you have a lot of saddles.
yes.
Now, is it clear which of them should be included? Like, is there a Stokes phenomenon or anything like that?
Oh, that's a fantastic question.
Thank you.
Let me take let me take up this question in a few slides, because it's going to be relevant there. I'll tell you everything I know about it, which is not much, but at least let me tell you that much. But there's a context to this after a few slides. Is that all right?
Perfect.
Okay. So now, so here's a lemma. So you take an action of the type that that we're discussing, pure two-particle interaction. Uij is ui minus uj, and now you look at the saddle point equations. So du of s equal to 0. The potential that I'm going to talk about will not be holomorphic or meromorphic. Therefore, you have two separate equations, one for u and one for u bar. And there's an assumption that v is even. That's true, and that v is periodic with period tau, period t, where t can be complex. Okay, so there's some setup. And here's the lemma. The first part of the lemma is that the uniform distribution of eigenvalues between 0 and the period is a solution of the variational equations. This is you can show this in 2 lines. And then the second part of this lemma is that the action of this uniform distribution is just equal to the average value of the potential between 0 and t. Okay, this takes 3 or 4 lines to check. Okay, these two are, if you want, homework problems, and they're very easy to check. I'm going to use this lemma. So now remember that I said that V is not meromorphic. So, and I'm going to change, sort of go to a complex point. So one needs a separate argument for a contour deformation. This is more subtle. We wrote this in the paper, but roughly speaking, what happens is that at the initial point, namely the initial contour of the matrix model, and at the saddle point that I find, you can replace the potential that I'm going to use by a meromorphic potential. Okay, and therefore, all along the contour deformation, you can use meromorphy up to things like wall crossing and so on, which was also related to Nati's question. But that's roughly what this argument is. Okay, the details are in the paper. I can tell you later. Now, the potential. So let's try to now apply this lemma, and you look at this potential. So you write this matrix model. You write it as this. I've pulled out a constant factor, which is not important. This carries very little entropy. The rest of the action can be written in terms of these functions called elliptic gamma functions. Okay? Despite the name, they're not quite elliptic. They're only quasi-elliptic. So what that means is that when z goes to z plus 1, the action is periodic. But when you go to z plus tau, it's not periodic, but just about not so. So the lack of periodicity is controlled by the Jacobi theta, the odd Jacobi theta function, okay, theta. So it's well understood what it is. But the fact is that it's not periodic, so we can't use our lemma as such. So what Alejandro, sorry, I should have said, so this part of the talk is based on a paper that I wrote about a year ago with Alejandro Cabo Bisset. Okay. Now, what we did was to deform this model, this potential, to different potential. Okay? So instead of this elliptic gamma function, I'm going to construct a function called capital Q, which is some dressed version of this. I have some theta naught here. B3 is the Bernoulli polynomial. Okay, Z is Z1 plus Z2. Notice that there is a Z2 here. So this is not meromorphic explicitly. And now the fact is that on the original contour of integration, Q is equal to 1 over gamma. Then the way, so this is engineered, is such that the absolute value of Q is actually doubly periodic. Okay, so in the horizontal direction, there's nothing to check. And these factors are rigged up to make it doubly periodic along tau. Okay, these two are easy things. And now this is sort of a very unexpected thing if you don't know about such things, namely that this Q function that I just talked about has this very interesting property, namely, if you look at this first equation over here, oops, sorry, the first blue box over this one, It's almost a modular form. Okay, what that means is that if you write the q at -1 over tau minus q at tau times tau, you don't get 0, but again, the lack of modular transformation is controllable. And this function f is a well-known, well-understood function. This is just a regular Eisenstein series, non-holomorphic Eisenstein series of weight 1, 2. Okay, and this function was first studied in the 70s by Bloch and Wigner. This is neither the Bloch that we know nor the Wigner that we know. They're both number theorists. And this formula is actually a very famous formula in number theory. It goes by the name of Bloch formula. And a lot of work has been done since then on this, and for reasons completely unrelated. It's something called algebraic K-theory, which I don't understand. But for us, the main point is that if you stare at this first equation, out of that, you can get a Fourier expansion for the function log of q along the lattice in a double Fourier expansion. So this function here is just a Fourier expansion along Z1 and Z2. Okay, so it's periodic. Good. So that's the technical part. Now let me tell you what's the point. So in this way, we can extend the action to a doubly periodic function. Okay. So if you didn't follow the technical points, let me say what we did. So you extend the action to the complex plane in such a way that you don't change the value of the partition function. The fact now that you have a doubly periodic extension means that you can just apply our lemma, and then there's a family of saddles labeled by m, n. And the action of the saddles need the average value of the potential. You have a Fourier expansion, you just read it off. Okay, so this is the answer. So you just get a simple rational function, cubic divided by quadratic. And in particular, for 1, 0, you get on the nose this black hole entropy function, the canonical function for black hole entropy. Okay. So now you have a bunch of saddles, so you can do the following. You fix some tau, and you ask which of these actions dominate. Okay. Which the real part of the action dominates. So this is sort of very, is much less sophisticated than what Nati was asking. So let me first do this. And clearly around tau equal to 0, it's this that dominates. So here's the first plot. So near tau equal to infinity, you just actually get pure radius space. When you go down towards tau equal to 0, the black hole starts to dominate. This picture has a symmetry between this, around this vertical axis. So everything is sort of mirrored. This is where the black hole starts to dominate. But in fact, if you look here, near other rational points, minus n over m, you get other solutions which dominate. So this is tau, the imaginary part of tau is 0.1. If you go down further, what you'll see is that other things dominate. Okay, I'll come to this formula in a second. And here is the picture. So it's a very rich picture. Around every rational point, you see some new phase that appears. Ion, are you going to remind me about time now, saying that I'm almost out of time?
Well, you have 7 more minutes, 5 to 7 more minutes.
Oh, even before the question time?
Yeah.
Okay, then I'm much more relaxed. Sorry, I put a timer, but never mind. That's fantastic. So I'll go a little slower then. Okay, so this is, here what I've done, let me repeat. I fixed a value of tau. I scanned over all the phases and just asked the computer to say which one dominates. Okay. Of course, that's not quite right, because I have to make sense of this infinite sum, and I've not done that. Okay, so all I've done is to essentially tell you near each rational point, I give you. So the way I should think of this formula over here, it's not an equality, but instead, near each rational point, I'm giving you the complete perturbative expansion. What this means, so how to proceed here? So of course, the right way is to do some kind of a Picard-Lefschetz theory or something like this. Now, I don't be done, as Ashok was saying this morning, these things are hard, but maybe it's possible. I haven't done this analysis, but there's something simple which you can already notice, namely that when 2 of the actions are equal, then you have to do something, 2 or more of the actions are equal, then immediately you shouldn't trust this formula, because then there's a macroscopic interference effect. Okay, what you should do then is look at the phases carefully and see what happens. When you do that, this picture actually changes slightly. And in particular, the region over here where my arrow is changes, and the black hole phase actually dominates a little more all the way it comes to here. Okay? That's as much as I can say about this infinite sum. That's I can say a little more, but only if pressed. So does that answer your question, Nati?
Yes, it does, and it's beautiful. But I'm puzzled by something else. And since you asked me, you gave me the floor, I will ask it.
Please.
Is it physical to have so many saddles?
Good. So the natural question is, what is the meaning of the saddles? So, yes. So from Yang-Mills theory, it's just what the matrix model gives me. Okay, so the question, for me at least, is what is the gravitational meaning of these saddles? Let me remind you that this is not such a new phenomenon. In ADS3, not exactly, but at some level of approximation, exactly the same thing happens, namely that there's an infinite set of saddles labeled by two integers m, n, and there's some kind of modular transformation which relates these two, the Malder-Sena-Strominger family of black holes, Euclidean black holes. Okay. Of course, we know that only two of them are Lorentzian solutions, the ADS3, thermal ADS3, and the BTZ black hole. Here, so far, we only know also only thermal ADS5 and the ADS5 black hole. The story is more complicated because they're not modular transformations of each other. But what I will say is, I'll turn it around. I'll say that I'm predicting an infinite number of solutions to Euclidean gravity with the boundary conditions that I tell you, okay, with the action that I've already written. Okay. I have an idea of what these solutions are, but I mean, many people have an idea. But nothing is understood so far. But it's not so exotic, what I'm saying. Okay, so I'll continue unless there's unless you want to say something more.
Just that it is fascinating.
Thank you. I agree. Let's continue then. Then in the last 5 minutes, I want to change topic. So I'm going to ask this question. What are these operators? So if you look at some basic ADS CFT sort of 101, we all are taught that at infinite n, if you look at the BPS spectrum, the single trace operators are single gravitons. Okay, this is without doubt. Now you can lift that to a statement saying that at infinite n, multi-trace operators are multi-gravitons. This is more subtle because you have to sort of explain what this means. What is the order of limits? But suppose I take n to infinity first, and there's a sense in which this is true, and this was explained in all these papers, and in particular in this nice paper by Chang and Yin. So in particular, at infinite, you can construct a class of operators in super Yang-Mills theory, which are in complete one-to-one correspondence with the class of supergravitons in ADS5. This essentially follows from group theory. They're all super conformed descendants of the identity. Okay. Now, in this paper, what they did was they actually said that when you start decreasing n from infinity, that no new operators or states come into the spectrum. Okay, and they check this to the first few orders. But that seems to be in tension with what I've been telling you so far, that the black holes have many, many more states, or much more entropy than the graviton, which you see here. All right. So how do you sort of reconcile these two facts? And this I like very much. So the fact is that the finite n, if you look at the finite n index, it's actually an interpolating function. Okay. So here is a table. The horizontal line is the charge n. The last row is the index of multi-gravitons in blue. These rows are the Yang-Mills theory index for rank 2, 3, 4, 5, 6, and so on. Okay, and what you see is that for the first two n plus 1 values, n being the rank, the index of the Yang-Mills theory is exactly equal to the index of the gravity. So here you see 5, 7, 9, etc. And after that, it starts to deviate. All right, so this is experimental. So this is super small values of charges, very small values of charges, which live somewhere here on this graph. You don't even see it. The red line is gravity now. And now the Yang-Mills theory agrees with the gravity for very small values of charges. Then it dips down, as you can see here. It actually becomes less than the gravitational index, and then crosses again and climbs up. And over here, it meets the black hole curves. Okay, so there are three regimes. This is the very small values of charge. This is sort of medium values of charge, which I can get until a computer. Now I can get until 400 or 500. And these are theoretical predictions for very, very large values of charge. Okay? So the figure I showed you here lives very, very close to the origin. Okay, so there's a beautiful interpolation, and this you can prove. Okay, and in order to prove this, you have to rewrite the problem, the index, in terms of this sort of Gross-Taylor type string. It's not the same as Gross-Taylor, but it's something like that. So what you do is you have this exponential of trace u dagger. You expand it. You have an infinite set of terms. Each term, this is my last slide, by the way. Each term has some products of trace u, so products of trace u to some powers, and similarly with u dagger. These products, there's a classical Frobenius formula. It says that you can rewrite these products in terms of characters of the UN theory. This is what this is chi tilde. Remember that the characters of UN are labeled by the partitions, which are called lambda of n. And the Frobenius formula says that the coefficients of that expansion are also characters, but of the symmetric group, which are also labeled by partitions, remember. Okay, so P here is a permutation or partition. So there are too many partitions, remember. So there are three roles that partitions are playing. One is that they label the characters of UN. They also label the characters of the symmetric group, but they also label the elements of the symmetric group. The last part is just a coincidence, only for the permutation group. And there's no deeper meaning to that. But here it is. So the permutation P can be just read off from the cycle shape. And this is the formula. And the formula says that you should restrict to Young tableau, which have rows at most n. Okay, so you have such a formula for U. Similarly for U dagger, you write it, you integrate over U. You have the orthogonality relation of characters. You can just integrate out U and get a formula for the index, which is written purely as a sum over partitions. Okay, two partitions, so partitions P and as well as lambda. And now there's no unitary matrix at all. This is completely explicit. You can put this on the computer very easily. And now you see here that when the rank n goes to infinity, then you're summing over all partitions. When you're summing over all partitions, then there is a second orthogonality relation of characters of the symmetric group, and using which this part of the expression becomes 1. Okay. Therefore, you're just left with only a sum of over partitions of this index function of the partition. Okay, so some kind of product, which you can very easily resum into an infinite product. Okay, so that's the index function at infinity. But now if you actually write it out, you'll see that this infinite product can be very easily identified with the multi-graviton partition function. Okay, and everything that I said can be repeated if you're slightly more careful, not necessarily for n equal to infinity, but for finite n. But then the argument only is valid for charge less than or equal to 2 times the rank plus 1. That's what I showed in the tables. Okay, and it's the same proof. This sort of small miracle that this gauge theory quantity on the left is equal to a multi-graviton object on the right was actually noticed in the original papers, but the interpretation was different. Okay, so here I'm saying this is actually true at infinite n and only true at infinite n. Okay. So I think I'm out of time. Let me then just leave you with some questions. There are many questions. One of them was already asked. What is the meaning of all these other saddles? In other words, there's a prediction. Can you find these solutions in gravity? There is a lattice and a torus which underlies the system. This reminds you of in many other beautiful works like Cyber-Witten theory or similar things. There's some underlying torus can we make sense of this torus in a deeper way? I don't know yet how to do that. For those of you interested in this, I'm very interested. One question is, this help from number theory, is it just some technical help that we're using? Or, I mean, I should say one thing. The reason these functions were sort of originally developed in number theory has to do with some, one of the deepest parts of number theory, L functions and sort of values of L functions. And so one question is that just an accident, or can we make a statement that the Yang-Mills partition function at algebraic values of tau is actually some L function value? So if there's something like that, then there is something very, very deep underlying this whole system. And then finally, I'll leave you with this last question, which is what I began the talk with, namely, can you identify the string theory, the sum over partitions as string theory? Is it a string theory? If it is, it's very interesting because it's actually capturing black holes. Thank you very much.
Thanks, Samir. Wonderful talk. And we can take more questions now.
Samir, can I ask a question? Sunil here. I thought a few slides back you said something about 4-dimensional Euclidean black hole solution that went by a bit fast. Can you just make the statement what you're conjecturing?
Was this in response to Nati's question? Is that what you're talking about?
I don't think so, actually. You said something about there being, I got the impression there's something like an SL2Z family of...
Precisely. So that was in response to Nati's question. Okay. So here are all these solutions in the gauge theory, right? Mm-hmm. For every m comma n, there is a solution, and there's some quasi formula. So I'm working on sort of promoting this into a formula, but so far not. You have something like this. And I'm just saying, so the left-hand side here is the matrix model or the Yang-Mills theory partition function. Mm-hmm. And I'm saying that there is an infinite number of saddle points. I'm telling you what the entropy or the free energy of each saddle point is. Mm-hmm. And the natural guess is that the best guess, nicest guess, is that each one of these saddles should have an interpretation in 5-dimensional Euclidean ADS gravity with asymptotic ADS5 boundary conditions.
And is this like a Poincare sum over those?
So I was too fast when I said this. In ADS3, so yes and no. So if you look, well, let me now go back. M and N are precisely lattice points, and there is an SL2Z transformation which relates them. Okay. All right. In this sense, it's analogous to what you're saying and what people know in ADS3 and in CFT2. Mm-hmm. Here, the analogy ends because S of m comma n is not exactly the modular transformation in the sense that we know in CFT2.
I see.
So in other words, if I translate this to gravity, it's not true. So in ADS3, the answer was particularly simple. If you were Maldacena or Strominger, then it's very easy to just realize that in Euclidean quantum gravity, in ADS3, the only solution is sort of pure ADS3 locally, and therefore the only sort of distinguishing feature of the solution is the choice of time.
Right.
In other words, the choice of contractible circle.
Right.
Okay? And all of them have locally the same curvature. Here we know that that's not the case.
Okay.
But this analogy may be pushed forward a little more. It's not the case because ADS5 doesn't have the same curvature as ADS5 black hole, unlike for BTZ.
Correct. But you're conjecturing that this sum is over 5D Euclidean black holes, exactly. Whatever they might be.
Exactly. Well, no, so let me refine that. So first, let me say gravitational solutions. Now you have to look at the entropy. If you look at the entropy formula, it turns out that when m plus n is 0 mod 3, the index, so the free energy is 0 to leading order. That's because this function becomes 0, so there is no, you'll see, you can work that out. That's a homework problem. But if m plus n is 1 or 2 mod 3, then this has very large entropy. So for those I would call black hole-like, or in other words, I expect a horizon.
I see.
Of course, these are Euclidean solutions, but so I expect some kind of a cigar-like.
Okay, thank you.
Mm-hmm.
Okay, so maybe one more question before we end the day. Okay, if not, then thanks, Samir, and hope you can visit our campus again. And that goes to all our other speakers of the day. Thanks for being here.
Thank you.
And, okay, so we then say end of the day, and then bye to all of you, and see you tomorrow for Sunil's talk at 9 in the morning. Bye.
Oh wait, there's a question. There's a question.
Oh, is there one?
I think so. Shingo, sorry, I can't.
I can't read. I can't see any
Shingo
question.
Takeuchi. Someone. Is that
sorry,
correct?
sorry. I mean just bye bye.
Oh, sorry.
Sorry.
Okay.
Thank you very much for your talk. Okay, see you tomorrow.
Bye bye.
Bye bye.